A whisper in the dark, a void so vast, so silent it almost feels alive. Yet it might be nothing at all, or is it everything? For centuries, humanity has pondered this. How can nothing give birth to everything? The idea seems impossible, yet the universe itself might hold the answer. Scientific revelations shattered old beliefs, revealing that from an unfathomable chaos, space and time burst into existence in a cosmic lightning strike. The Big Bang wasn't just a moment, it was an explosion from absolute nothing. But what is nothing really? A blank canvas? A paradox? As we unravel the secrets of existence, one question lurks in the shadows. If everything came from nothing, what are we truly made of? The answer might reshape our reality and challenge everything we thought we knew. As we prepare to journey millions of light years away to witness this cosmic marvel, let's ground ourselves for a moment. I'm fascinated by the idea of us all watching this from our tiny corner of the universe. Let me know in the comments what time it is where you are and whether you're watching this under sunlight or starlight. And if you're ready for the voyage, hitting that like button and subscribing tells me you're on board. When we try to understand the origin of everything, we first need to grapple with the concept of nothing itself. In everyday life, nothing might mean an empty space, a void without objects, or a lack of activity. But in philosophy, the idea runs much deeper and more complex. Philosophers ask, what does nothing truly mean? Is it merely an absence of matter, energy, space, or even time? Or is it something else, an idea that defies our usual understanding? Many thinkers have debated whether nothing is even coherent. Some argue that nothing is impossible to conceive because our minds tend to think in terms of something rather than nothing. Imagining absolute nothing often results in the mind filling the void with thoughts or images, creating a paradox. Our cognitive structures seem incapable of truly grasping nothing, making the concept more a philosophical puzzle than a straightforward idea. Historically, distinctions have been made between different kinds of nothing. The ancient Greeks distinguished between the void and matter. Aristotle, for example, rejected the idea of a true vacuum, suggesting that nature abhors a vacuum. In his view, nothing or the void was impossible because a space devoid of substance would be immediately filled. This perspective shaped centuries of thought, making the idea of pure emptiness seem nonsensical. In modern philosophy and science, the concept evolves further. In metaphysics, some interpret nothing as the absence of all entities, no objects, properties, space or time. This absolute nothing is a state where nothing exists. No matter, no energy, no dimensions. But this raises a paradox. How can something emerge from nothing? If nothing is truly devoid of everything, how could anything, including the laws of physics, arise from it? Many philosophers ponder this question. Some suggest that nothing at the universe's origin might have been a different kind of nothing, perhaps a quantum vacuum. This state seems empty, but is full of potentialities due to quantum fluctuations. These fluctuations can produce particles and energy spontaneously, blurring the line between nothing and something. Consequently, asking what came before the universe is often seen as a category mistake because before might not be meaningful when discussing a state of nothing. Others argue that the concept of nothing itself is unstable or illusory. Our language and thought are built around distinctions. There's something and there's nothing. When we speak of nothing, we inadvertently reintroduce something. Heidegger proposed that nothing is not just the absence of beings, but a fundamental aspect of reality, revealing itself during moments of change or crisis. In this view, nothing isn't merely empty space, but a necessary counterpart for understanding being. Some modern perspectives challenge whether nothing even exists as a true state. They see nothing as a human construct, a concept used to designate a lack, but always involving some conception of something. This raises questions about whether nothing is more of a placeholder, an idea held onto rather than an actual reality. Thus, the concept of nothing in philosophy is complex and tangled. It challenges our intuition, language, and understanding of existence. Is nothing an absolute void, completely devoid of everything, or a potential, something not yet actualized? Is it even meaningful to talk about nothing when our thinking is structured around something? These questions remain central to philosophy's pursuit of understanding origins, from the absence of everything or something entirely different. They push us to reconsider what we know about reality and the nature of existence itself. Throughout history, the concept of nothing has bewildered and fascinated cultures and thinkers in equal measure. For some, it has been a void, an emptiness so profound that it defies definition. For others, it has been a fertile ground of potential, a beginning from an infinite realm of possibilities. These interpretations weave a complex tapestry, reflecting humanity's deep curiosity about existence and non-existence. In ancient Greece, the notion of nothing was a subject of philosophical debate. Aristotle saw nothing as a privation, a lack or absence, something that exists only in relation to something else. To him, nothing was not an entity in itself, but a concept that arose when something was absent. The Greeks, in their quest to understand the universe, often sidestepped absolute nothing, instead focusing on the nature of being and becoming. For them, the question was less about nothing, and more about what being truly was, as they believed existence was a fundamental substance or essence that underpinned reality. Moving eastward, ancient Indian philosophy approached nothing through the lens of spiritual and metaphysical ideas. Many schools considered nothing as a state of transcendence, a realm beyond physical existence. In the Upanishads, the concept of neti, not this, not that, signifies a process of negation, stripping away all that is perceived until only pure consciousness remains. Here, nothing isn't a void but a space of potential, where all forms dissolve back into a singular, formless reality known as Brahman. It's a peaceful silence, the source of everything, and yet itself unintelligible in the conventional sense. In medieval Europe, Christian scholars grappled with nothing from theological perspectives. To many, nothing was linked with the concept of creation ex nihilo, out of nothing, which became a cornerstone of Christian doctrine. The idea posited that God, an omnipotent being, brought the universe into existence from a state of absolute nothingness. This notion was revolutionary because it emphasized divine power, creation without pre-existing materials, highlighting the divine's ability to summon reality from the void. Philosophers such as Augustine pondered whether nothing even truly existed, or whether it was simply the absence of being, emphasizing that only what exists has any real substance or reality. Beyond philosophical and religious interpretations, the scientific perspective on nothing has evolved dramatically, especially with the advent of modern physics. The classical notion of nothing as a complete void was challenged by discoveries in quantum mechanics. Physicists now describe a quantum vacuum, a state that is far from empty. Instead, it teems with fleeting particles popping in and out of existence, governed by the strange laws of quantum fields. In this view, nothing isn't a true nothingness, but rather a seething, dynamic backdrop that underpins reality. Throughout this journey, the idea of nothing has often been bent and reshaped to fit the needs and understandings of diverse cultures. For some, it is a void, an emptiness to be filled or avoided. For others, it is a fertile emptiness, full of untapped potential and the origin point of all that exists. Some see it as a divine act, an act of will and power that births the universe. Still, others perceive it as a subtle, ephemeral state, one that exists only in the mind or in abstract thought. Despite the differences, a common thread weaves through every interpretation. Nothing is never just nothing in the conventional sense. It is a mirror held up to the universe itself, a reflection of what lies beyond our perception, what precedes creation, and what might ultimately exist in the depths of reality itself. Facing nothing is confronting the limits of understanding, the edge of existence, and the wellspring from which everything flows, whether divine, metaphysical, or scientific. It's both a mystery and a fundamental concept, a blank canvas and a cosmic seed. Considering nothing takes us into a realm that defies everyday understanding, a space where nothing exists, yet the concept itself is difficult to grasp. Is nothing a real, tangible state, or just an illusion created by our minds to understand the universe's beginning? To explore this, we examine philosophy, physics, and linguistics. Humans conceptualize nothing through language built around a binary of something and nothing, helping us describe our world. When we say nothing exists, we usually mean the absence of matter, energy, space, and time. But is such an absence even possible? Or is nothing merely an idealization, an abstract concept used to frame questions about origins. Philosophically, many debate whether nothing can genuinely exist outside human thought. Immanuel Kant argued our minds are structured to perceive and understand existence itself. Thus, nothing as a state might be impossible because imagining nothing inevitably involves referencing something. When we imagine nothing, we fill it with absence, making it into a kind of thing. If consciousness cannot conceive of nothing without something, is nothing even a valid entity? Physics offers insights, especially from quantum mechanics and cosmology. The classical idea of nothing as a complete void, an empty space without particles or energy, raises questions. Can such a state exist? Quantum physics suggests not. Instead of a barren void, what we observe are quantum fields with continual activity. Even in empty space, particles flicker in and out, driven by the uncertainty principle. The vacuum isn't truly empty, it's a dynamic quantum foam. This quantum foam suggests nothing might be an illusion, more an approximation than a fundamental reality. According to the Big Bang theory, the universe didn't emerge from absolute nothing, but from a quantum fluctuation, or a highly compressed, unstable state of spacetime. In this view, nothing is nonsensical because the fabric of space and time was already in a limbo, a pre-entity beyond classical understanding. If nothing is impossible, what does that imply about the universe's origins? It suggests asking what existed before the Big Bang may be flawed, a question like asking what's north of the North Pole. The boundary between nothing and something might be a conceptual rather than a physical boundary. Some cosmologists propose the universe arose from a quantum vacuum, a state not empty in the classical sense but filled with potential. In this framework, nothing is an unstable baseline, not a void, but a fertile ground of possibilities. Rather than a true absence, it's a transition, more a state of potential rather than an absence of everything. Even in speculative models like the multiverse, nothing remains elusive. Each universe could originate from a fluctuation or a bubbling of a larger cosmic fabric, not from nothingness. We may realize that the idea of nothing itself is misleading. It's less a state of absolute emptiness and more a human construct used to distinguish what is known from what is unknowable. Ultimately, seeking nothing might be a human attempt to understand the origin of everything, a tempting but flawed quest. Instead of nothing, what we seek might be a deeper understanding of potentiality, the undefined state from which all matter and energy emerged. The universe begins not from absence, but from a realm where concepts of existence and non-existence blur. Reality is a dance of potentialities waiting to unfold. In the end, nothing may be an illusion, an idea that helps us differentiate the known from the unknown. Rather than a true void, nothing might serve as a conceptual boundary. The universe's origin could be better understood as a shift from potentiality to actuality, where the division between nothing and something is only perceptual. Attempting to find nothing may be inherently human, part of our desire to find origins in absence. Still, the true beginning may lie not in the void, but in a state of infinite possibilities, a domain where boundaries between existence and non-existence lose meaning, and reality unfolds from a fertile ground of potentialities. When contemplating nothing, we confront one of the most profound questions about existence. What does it truly mean for there to be nothing? Our minds often picture empty voids, vast spaces between stars, the absence of matter, a black hole's emptiness, or the emptiness after something is gone. Yet, these are idealized or practical notions of nothing. The core issue digs deeper into the fabric of reality and our understanding of existence itself. The implications of nothing are vast, affecting philosophy, physics, and metaphysics. If nothing truly exists, then the concept of existence or somethingness becomes mysterious. How can anything arise from nothing? Is that even possible? Alternatively, the idea of nothing may be inherently flawed because defining it introduces some form of something, a paradox. In everyday life, we accept that objects, rocks, trees, people, exist. But physics challenges this assumption at a fundamental level. In quantum physics, what appears as nothing is actually filled with quantum fluctuations, temporary particles emerging and vanishing. This makes nothing in a quantum vacuum far from absolute emptiness. Instead, it is a seething ground of potentiality. Even empty space isn't truly nothing but a fertile space for emergence. When scientists explore the universe's origins, they ask, what came before the Big Bang? Was there a before? Some theories suggest that asking what existed before makes no sense because time itself began with the Big Bang. If so, nothing as a prior state may be meaningless, since both time and space sprang from that event. Understanding nothing then becomes a quest to grasp what preceded or underpins the universe, an understanding that might ultimately be beyond human comprehension. Philosophers also debate nothing. Some argue it is impossible, an absolute void that cannot truly exist because conceptualizing it generates negativity that resists full definition. Others see the universe's emergence from nothing as a profound mystery, a hint at a deeper, possibly divine principle. If all comes from nothing, the lines between creation and chaos blur, and the universe appears as emergence from non-being. Questions then arise. Does nothing have ontological reality? Does it exist independently? Or is it merely the absence of being, a relative concept? If nothing has no properties, no energy or information, then asking whether it can generate something becomes paradoxical. It might not be a state of non-existence, but a neutral background from which potentialities emerge, or not at all. This neutral nothing may be a canvas, possibly the indeterminate ground of all potentialities or none. Contemplating nothing pushes the limits of human knowledge and perception. Our minds recognize patterns and seek meaning in existence, but nothing defies these patterns. It challenges our logic and intuition, raising the possibility that the universe's existence is an inexplicable accident, a spontaneous emergence from non-being that we may never grasp fully. Furthermore, nothing invites us to reflect on the relationship between existence and non-existence. If something exists, nothing does not. But does nothing exert influence? If it holds no properties or potential, it can't be an active force. Still, the concept of nothing sharpens our understanding of something. Without nothing, the idea of existence loses context and significance. These implications extend to the nature of reality, consciousness, and our place in the cosmos. If everything emerged from nothing, then nothing might hold the key to the universe's deepest secrets. Exploring nothing may be the path to understanding the origins of everything. Or perhaps nothing is a philosophical placeholder, more an idea than a real state. Ultimately, nothing is like a shadow cast by the mind, faint and elusive but profoundly important. It guides us into a realm of mystery where understanding dissolves. Grappling with nothing confronts the edges of reality, where the void pushes against existence itself. In that push, the universe's deepest secrets might lie silently, waiting. Reality, with all its complexity, may be born from the simple, profound idea of nothing. The concept of nothing isn't just a blank space or an emptiness. It's a profound puzzle that has fascinated philosophers and scientists alike. In modern metaphysics, this idea challenges what it means for something to exist at all. When we talk about nothing, we're often imagining a vacuum, void of matter, energy, space, and time. But that simple image quickly becomes complicated the moment we begin to scrutinize it. Historically, many thinkers treated nothing as the absence of everything, an absolute void where no laws hold sway, no particles exist, and no potential for change persists. Yet, as our understanding of physics deepened, particularly with the development of quantum theory, the notion of nothing took on new dimensions. It's no longer a mere empty space, but a state teeming with potentialities. Virtual particles flickering in and out of existence, energy fluctuations, and quantum fields that pervade all of space. This subtlety reshapes how modern metaphysicians approach nothing. One of the main ways nothing influences modern metaphysics is through the question, if nothing truly exists, could it be the origin point of everything? Philosophers and physicists grapple with whether a state of absolute nothing is even stable or conceivable. Some argue that nothing is impossible, because even the slightest quantum fluctuation would generate something. If quantum fields can spontaneously give rise to particles, then nothing might be more like a something, a state with inherent potentialities. This leads to a controversy. Did the universe come from absolutely nothing, or from a kind of something that is fundamentally different from ordinary matter? Furthermore, the debate around nothing challenges our understanding of causality and the foundation of reality. Classical metaphysics presumes that everything has a cause, but if the universe emerged from nothing, then causality itself might be an emergent property rather than a fundamental principle. Some thinkers propose that nothing is prior to causality, or that causality only makes sense within the realm of something, the universe itself. In this view, the concept of nothing isn't just an absence, but a crucial part of understanding how the fabric of reality is woven. Modern metaphysics also considers the role of nothing when evaluating the nature of existence. If metaphysical nothing is not just emptiness, but involves the absence of potentialities, then the transition from nothing to something becomes a kind of puzzle. How does a state of non-being generate or give rise to being? This question influences theories about the initial conditions of the universe, the fine-tuning of physical constants, and whether the universe's existence was necessary or contingent. The notion of nothing pushes some philosophers to explore whether reality could be fundamentally different, or if nothing is an incoherent concept to begin with. Some argue that even contemplating nothing is nonsensical because mind and language are inherently tied to something. This philosophical stance suggests that what we call nothing might be a mental construct, a way to frame our understanding of absence, but not an actual state of reality. In summary, nothing acts as a spark that ignites countless debates in modern metaphysics. It raises questions about origins, causality, and the nature of existence itself. The deeper we peer into nothing, the more elusive and essential it becomes. What appears as a simple absence reveals itself as a central puzzle at the core of understanding how everything, from the tiniest particles to the vast cosmos, began. The search to grasp nothing isn't just about emptiness. It's about the boundaries of reality and the possibilities that lie beyond what we can conceive. Today's cosmology presents an astonishing and mind-bending picture of the universe, full of mysteries and debates. When scientists observe galaxies, cosmic background radiation, and space-time itself, they see a story that begins with the Big Bang. But what does that truly mean? And does it reveal where the universe came from? The dominant view among cosmologists is that the universe started about 13.8 billion years ago from an extremely hot, dense state, a singularity, where all space, time, matter, and energy were compressed into an unimaginably tiny point. From this state of nearly infinite density and temperature, the universe expanded rapidly in what is called the Big Bang. It's not an explosion from a single point into empty space, but rather a rapid expansion of space-time itself, stretching the fabric of reality. Imagine inflating a tiny invisible balloon. That's akin to what the universe did in its early moments. Initially, no structures like galaxies, stars, or atoms existed. Instead, it was a fiery soup of fundamental particles, constantly interacting and cooling as the universe expanded. Over billions of years, gravity caused these particles to coalesce, forming the complex cosmic tapestry we observe today. A key piece of evidence supporting this model is the cosmic microwave background radiation, the universe's faintest glow seen in all directions. This relic radiation, dating from about 300,000 years after the Big Bang, indicates the universe was once hot and dense. Its uniformity suggests a smooth, evenly distributed beginning, which aligns with the Big Bang theory. However, the concept of a singularity signifies that our existing physics, especially Einstein's general relativity, breaks down under such conditions. This indicates our understanding is incomplete. To truly grasp the universe's origin, we need a theory that unifies quantum mechanics with gravity, a theory of everything. Quantum cosmology proposes that before the Big Bang, what we call nothing might not have been a void but a quantum state, a fluctuation in a quantum foam that led to the creation of our universe. Instead of a singular beginning, the universe might have emerged from a quantum fluctuation, a spontaneous event rooted in a fundamental energy field beyond everyday cause and effect understanding. This idea hints that our universe could be just one bubble in a multiverse where countless universes are constantly forming, evolving, and fading. Another compelling notion is cosmic inflation, an ultra-rapid expansion occurring fractions of a second after the Big Bang. Inflation explains why the universe appears flat, homogeneous, and isotropic. that it looks similar in all directions. During inflation, tiny quantum fluctuations in spacetime were stretched to cosmic scales, setting the seeds for galaxy formation and large-scale structures we see today. Despite progress, many questions remain. What triggered the initial expansion? Was there a cause, or was it spontaneous? What existed before the Big Bang, if anything? Some models suggest a cyclic universe, where expansion is followed by contraction, an ongoing cosmic heartbeat. Others favour the multiverse, proposing our universe is a single bubble amid an ever-expanding multiverse. These ideas challenge traditional notions of origin, causality, and reality. Current cosmology offers a compelling yet incomplete narrative. It details the universe's evolution from a hot, dense state to the vast cosmos we see now, but doesn't answer whether there was a true beginning at all. Is nothing really nothing, or a quantum state brimming with potential, capable of giving rise to everything? As scientists explore spacetime's fabric and the quantum nature of reality, they move closer to understanding the ultimate origin. Yet, with each discovery, the universe's beginning, if a definitive starting point ever existed, appears more mysterious than we can fully comprehend. This ongoing story is written in the languages of physics, philosophy, and wonder, revealing that the true origin might remain forever beyond our grasp. The Big Bang Theory is one of the most accepted explanations for how our universe began. It proposes that, rather than emerging from a pre-existing state or a specific act of creation, the universe started as an incredibly hot, dense point, an infinitely small singularity, where all matter, energy, space, and time were compressed into a single, intense point. It's not a traditional explosion, but an expansion of space itself, stretching out from this primordial state. The story begins around 13.8 billion years ago, when this singularity started to expand, a process known as the Big Bang. It's crucial to understand that the Big Bang wasn't an event happening somewhere in space. Rather, it was the rapid expansion of space itself, bringing space and time into existence. Before this event, the concepts of before are problematic because, according to Einstein's theory of general relativity, space and time are interconnected into a fabric that can be stretched, warped, and influenced. If no space existed prior, then asking what happened before the Big Bang is meaningless, challenging our fundamental understanding of reality. Initially, after the Big Bang, the universe was a hot, dense soup of particles, quarks, electrons, photons, that collided at near-light speeds. As the universe expanded, it cooled, allowing these particles to combine into atoms, mainly hydrogen and helium, the building blocks of everything that followed. Over millions and billions of years, gravity pulled these atoms together, forming the first stars and galaxies, creating the cosmic web seen today. A key piece of evidence supporting the Big Bang is the cosmic microwave background, CMB, the faint glow of energy left over from the universe's infancy. Discovered in the late 1960s, this residual radiation is like a baby picture of the cosmos, revealing what the universe looked like about 300,000 years after the initial expansion. Its uniformity and tiny fluctuations provide critical insights into the universe's initial conditions, endorsing the idea of a hot, rapid start. Another major piece of evidence is the redshift of galaxies. Observations show that galaxies' light has been stretched toward the red end of the spectrum, indicating they are moving away from us. The farther a galaxy, the faster it recedes, suggesting the universe is expanding. This observation is a sign that the universe was once much denser and more compact, supporting the Big Bang model. The theory predicts that, as we trace back in time toward the beginning, the universe's temperature and density become extremely high. To understand what happened in these earliest moments, possibly within the first fractions of a second, scientists investigate theories that unify quantum mechanics and gravity, such as quantum cosmology and string theory. These explore ideas like quantum fluctuations in a broader multiversal context, or propose that our universe might be one bubble in a vast cosmic foam. However, the Big Bang doesn't explain everything. It doesn't answer what triggered the initial expansion, or why the singularity existed in the first place. It also raises questions about what, if anything, preceded the Big Bang. Some hypotheses suggest our universe is part of a multiverse, or that the Big Bang was a transition from a prior cosmic state. As scientists continue to piece together our cosmic origins, the Big Bang remains our best explanation, supported by extensive evidence and scientific insight. Still, it opens deeper mysteries about the nature of existence, the universe's fundamental structure, and whether the universe's beginning was a unique event or part of a broader cosmic sequence beyond current understanding. The question of how everything started from nothing continues to inspire scientific inquiry and philosophical reflection, fueling our curiosity about the cosmos's profound depths. Imagine the moments immediately after the Big Bang, where the universe was an unimaginably hot, dense point, expanding and cooling rapidly in a fraction of a second. This is where cosmic inflation becomes crucial. It's a theory that helps fill in some of the mysterious gaps about how the universe transitioned from its initial, tiny, chaotic beginnings into the vast structured cosmos we observe today. Cosmic inflation suggests that, within the first trillionth of a second, a tiny fraction of a second, there was an intense burst of exponential expansion. Instead of stretching out gradually, the universe ballooned at a rate far faster than the speed of light, growing from subatomic scales to macroscopic sizes almost instantly. During this fleeting moment, space itself expanded so quickly that regions once connected and in contact suddenly became far apart. This rapid expansion might seem counterintuitive. Nothing can travel faster than light in relativity. But cosmic inflation doesn't involve objects moving through space faster than light. Rather, space itself is stretching. Imagine inflating a balloon with marks on its surface moving apart. Nothing is exceeding the speed of a light, but the space between points expands so rapidly that they become vastly separated. Why is this sudden burst of expansion so important? It helps explain some long-standing questions. One is the horizon problem. How different parts of the universe, so far apart that light from one side hasn't yet reached the other since the Big Bang, still look remarkably similar in temperature and composition. Inflation offers a solution. Before inflation, these regions were in close contact, reaching thermal equilibrium. Then, inflation stretched them far apart so quickly that they are no longer in contact, yet they still share properties because they originated from the same initial conditions. Inflation also addresses the flatness problem. Observations show the universe appears geometrically flat, similar to a sheet of paper rather than a sphere or saddle. Without inflation, tiny deviations from perfect flatness at the universe's birth would have magnified over time, leading to a curved universe today. Inflation flattened out any such initial curvature by stretching the fabric of space so extensively that the universe appears flat on large scales. It's like crumpling a balloon then inflating it. The surface smooths out, erasing wrinkles and bumps as it expands. Furthermore, cosmic inflation offers a natural explanation for the tiny fluctuations in density that grew into galaxies, stars, and planets. During inflation, quantum fluctuations, minute, random jitters at the smallest scales were stretched across the universe. These tiny variations seeded regions of slightly higher or lower density, guiding the formation of cosmic structures. Without inflation, explaining how the early universe developed such uniformity with the necessary ripples for structure formation would be difficult. Many questions about inflation remain. What caused the rapid expansion? Was it driven by a new energy called the inflaton field? Could inflation have continued indefinitely in some regions, leading to a multiverse, a vast collection of universes, each with its own laws? These ideas challenge our understanding, pushing us to reconsider what nothing really means. As we reflect on the universe's origins, cosmic inflation shows that the earliest moments of existence involved forces and phenomena that defy everyday experience. It provides a compelling narrative connecting the tiny, mysterious beginning with the expansive universe we observe today, all rooted in physics that continues to be tested, refined, and explored. The story of inflation isn't just about expansion. It's about the birth of structure, order, and perhaps even meaning emerging from primordial chaos. Certainly. Here is your shortened text, precisely 632 words. There are alternative models to the traditional Big Bang theory that aim to explain how our universe might have come into existence, or differ from the standard narrative of an initial singularity exploding into space and time as we know them. One intriguing alternative is the oscillating universe model, also called the cyclic universe. Imagine a universe cycling through endless phases of expansion and contraction. Instead of a one-time event, a singular explosion, the universe repeatedly expands from a dense state, cools, forms galaxies, stars, planets, and life, then slows, contracts, and collapses into a dense point. From this point, the cycle begins again. Think of it as a cosmic heartbeat, with each pulse renewing the universe. This model challenges the idea of a definitive beginning and suggests the universe is part of an eternal rhythm, oscillating between phases. While it addresses questions about what preceded the Big Bang, it faces challenges, such as explaining what triggers each cycle and how entropy resets or accumulates. Some theorists propose quantum gravity effects might produce a bounce instead of a crunch, avoiding a final collapse. Another captivating idea is the multiverse hypothesis. Here, a universe is just one in a vast, possibly infinite collection of universes. These universes could vary enormously, with different physical laws, dimensions, constants, or initial conditions. Picture a cosmic bubble bath, where each bubble represents a universe. Each comes into existence, expands, evolves, and sometimes disappears. The multiverse offers a new perspective, shifting the origin question from where did this universe come from to how did this universe become part of this vast collection. Some interpretations stem from string theory and quantum mechanics, especially the concept of eternal inflation. According to eternal inflation, some regions of space undergo rapid exponential expansion, creating pocket universes within an ever-growing multiverse. While compelling, the hypothesis faces challenges in testability. How do we observe or measure other universes? Nonetheless, it provides a framework for understanding the fine-tuning of constants in our universe, suggesting we are just one fortunate bubble among countless others. This brings us to chaotic inflation, a variant suggesting the universe underwent rapid exponential expansion, driven by a quantum field called the inflaton. In chaotic inflation, the universe can originate from a quantum fluctuation, a sort of cosmic roulette wheel. Some models propose the universe emerged from a quantum seed, fluctuating into a stable state and then inflating rapidly. This model strengthens the tie between quantum physics and cosmology, emphasizing randomness and probability as core to cosmic origins. Moving further into speculative physics, quantum gravity models, especially loop quantum gravity, propose that at the smallest scales, space and time are quantized, discrete loops woven together. Instead of a singularity, an infinitely dense point, these theories suggest a big bounce. As the universe approaches the conditions of a singularity, quantum effects prevent densities from becoming infinite, causing space-time to rebound. In this view, the universe's birth could be a rebirth from a previous contracting phase or a different quantum state, not the absolute beginning of everything. Similarly, brain cosmology, based on string theory, imagines our universe as a three-dimensional brain, floating in higher dimensional space. Collisions between brains, like two sheets colliding, could produce enough energy to spawn a universe. This brain collision model offers an alternative to singularity, viewing the universe's origin as a collision rather than an explosion. All these models show that the story of our universe's origin remains unsettled. They raise more questions. Some propose a beginning, others argue for eternal processes, and some see no clear start at all, favouring cycles or a multiverse. The common thread is their deep ties to the fundamental laws of physics, many still shrouded in mystery. Regardless of which model is correct, our quest continues, driven by curiosity, imagination, and a desire to understand the fabric of existence. Let me know if you'd like any further adjustments. Quantum mechanics, with all its strange and counterintuitive principles, plays a pivotal role in understanding the origins of everything from nothing. When traditional physics talks about the beginning, it often references the Big Bang, a moment where space-time, matter, and energy burst into existence. But what sparked that moment? Here's where quantum mechanics comes into focus, revealing a universe far more dynamic at its very inception than classical theories once imagined. At the heart of quantum mechanics is the idea that particles don't have fixed positions or velocities until they are measured. Instead, they exist in a cloud of probabilities, constantly fluctuating, appearing and disappearing in a dance of uncertainty. This inherent fuzziness challenges our intuitive notions of continuous, predictable reality. When we look back to the universe's earliest moments, we find that space itself was not a smooth, placid backdrop, but a frothing, restless quantum sea. Fluctuations at the quantum level, tiny, random wiggles in energy, become the seeds of all that we see today. Imagine that at some infinitesimal moment, the fabric of spacetime was a quantum vacuum, a state that was not truly empty but brimming with potentialities. These quantum fluctuations imply that even in what appears to be nothing, there are constant spontaneous variations in energy. Sometimes these fluctuations are so powerful that they can create particles out of seemingly nothing, virtual particles that wink in and out of existence within a blink of an eye. The quantum vacuum, far from being an empty void, acts like a bubbling cauldron filled with untapped potential energy. But how do these fleeting microscopic fluctuations give rise to something as vast and ordered as our universe? One leading idea is that, under certain conditions, quantum fluctuations could have been magnified during the earliest moments of cosmic inflation, a rapid, exponential expansion that stretched tiny quantum ripples into macroscopic density differences. These differences then served as the blueprint for the large-scale structure of the universe: galaxies, clusters, superclusters, all arising from the initial quantum irregularities. This process turns classical causality on its head. Instead of a cause and effect chain originating from a prior event, quantum fluctuations suggest that randomness and chance could have played a creative role. The early universe could have been born out of spontaneous quantum events that, once set into motion, amplified and organized themselves into the cosmos we observe today. The vacuum, instead of being truly empty, becomes a fertile ground for the birth of reality itself. Moreover, these quantum effects help solve a paradox. How can something come from nothing? Quantum theory shows that nothing, when viewed through a quantum lens, isn't a barren void, but a state filled with latent potential. It's a seething quantum foam, one in which the potential for all existence resides, waiting for a fluctuation to tip the scales and ignite cosmic creation. In essence, quantum mechanics and the story of quantum fluctuations suggest a universe founded on randomness, chance, and the inherent unpredictability woven into the fabric of reality. Instead of a universe that emerged from an absolute void, perhaps it emerged from a quantum sea teeming with unexpected possibilities, an eternal dance of potentialities constantly flickering into existence. It's a mesmerizing idea, one that challenges our deepest understanding of nothing, hinting that the very fabric of reality is woven from the unpredictable, and that the origins of everything might be rooted in the unpredictable dance of quantum particles and fields, a dance that continues to echo through the cosmos. Quantum physics peels back the layers of what we think of as reality, revealing a universe far more strange and interconnected than any classical picture could suggest. Instead of everything being set in stone, fixed and predictable, quantum mechanics introduces a universe that's fundamentally probabilistic and woven together by a web of uncertainties. At its core, it describes the very fabric of reality not as a smooth, continuous sheet, but as a frothing, dynamic tapestry, where particles flicker in and out of existence, and bits of energy fluctuate in a quantum foam. Imagine the universe at its smallest scales, so tiny that they defy our everyday intuition. Instead of solid objects with definite positions and velocities, particles such as electrons and photons behave like waves of probability. They don't have a single pinpointed location until we look for them. Instead, their existence is expressed as a spread of possibilities, what physicists call a wave function, that collapses into a specific state when we observe or measure. Until then, particles exist in a cloud of potentialities, existing in multiple places and even states of being simultaneously, thanks to the weirdness of superposition. What makes this even more astonishing is the principle of entanglement. It's as if particles are linked across the universe, so that the state of one instantly influences the state of another, no matter how far apart they are. This phenomenon defies the classical notion that nothing can influence something faster than the speed of light, implying that the universe is a deeply interconnected whole. Instead of isolated pieces bumping around randomly, quantum physics reveals an inseparable interconnected fabric, where the distinction between separate objects blurs into a collective network of probabilities. The essence of the quantum description of reality also involves the concept of quantum fields. Instead of particles being tiny, standalone spheres, Physics tells us that what we perceive as particles are actually localized excitations or ripples in underlying fields that fill all of space. Every particle type, electrons, quarks, photons, has its own field, and these fields are the universe's fundamental building blocks. When energy excites these fields, particles pop into existence or vanish back into the field, creating a universe that's a constant dance of emergence and disappearance at the quantum level. Then there is the quantum foam, a term coined by physicist John Wheeler, that suggests that at the Planck scale, space and time are not smooth but frothy and turbulent. On the smallest scales imaginable, spacetime itself might be bubbling with quantum fluctuations. Instead of a fixed stage for the universe to unfold upon, what we think of as space and time are emergent phenomena, arising from an underlying chaos of quantum uncertainty. In this view, the very fabric of reality is a restless sea of quantum activity, forever bubbling and shimmering. This quantum view brings to light a universe where the act of observation is not just a passive glimpse, but an active participant in shaping reality. The measurement process influences what exists, a concept that sends ripples into philosophical questions about the nature of reality itself. Is the universe, in a sense, dancing on the edge of potentiality, collapsing into certainty only when observed? Ultimately, quantum physics suggests that at its deepest level, reality is a vast interconnected cloud of probabilities. It emphasizes that what we see, solid matter, objects, even the fabric of spacetime, is fundamentally emergent from a web of quantum fields and fluctuations. Everything we perceive springs from an underlying quantum fabric, mysterious and intricate, yet fundamentally woven into the fabric of the universe. It is a universe that is less like a clockwork mechanism and more like a sprawling, shimmering mosaic of possibilities, each piece connected, each piece dancing to the tune of quantum indeterminacy. To truly grasp the origins of everything, we need to understand the fabric in which the universe exists, space-time. Think of space-time as the cosmic stage where all events unfold, a four-dimensional continuum blending the three familiar dimensions of space, length, width, height, with time itself, intricately woven together into a seamless fabric that stretches across the universe. But what exactly is space-time? At its core, space-time is not just empty emptiness. Instead, it's a dynamic, malleable medium that interacts with matter and energy. Unlike the static backdrop of a theatre, space-time responds, bending, warping and flowing, shaped by the mass and energy within it. This idea was revolutionary, arising from Einstein's theory of general relativity, which proposed that gravity is not merely a force pulling on objects, but a consequence of how mass and energy tell space-time how to curve, and how that curvature guides the motion of objects. Now, the question of how space-time itself originated is a profound puzzle, an inquiry that touches the very limits of human understanding. Many scientists and cosmologists believe that space-time came into existence at the birth of our universe, during the moment we call the Big Bang. But here's where things get tricky. The Big Bang wasn't just an explosion of matter and energy into pre-existing space and time. Instead, it was the very beginning of space and time as we understand them, emerging from an initial state of unimaginable density and temperature. So, how can something come from nothing, especially something so fundamental as space-time? To explore this, we need to venture into the realm of quantum cosmology. Quantum theories suggest that, on the tiniest scales, far smaller than an atom, space-time itself isn't smooth and continuous, but frothy and fluctuating. These quantum fluctuations can give rise to tiny, momentary distortions in the fabric of space, which, under certain conditions, might have grown into the universe we observe today. Some cosmologists propose models like the quantum creation of the universe, where space-time emerges spontaneously from a quantum vacuum, a state of no classical matter or energy, just a seething, restless field of potentiality. In this picture, nothing is not a simple void, but a quantum event, a bubbling probabilistic process where space-time pops into existence from a state of pure possibility. The laws of quantum mechanics imply that even from nothing, something can come into being, if only briefly, by virtue of chance and the strange rules of the quantum world. One of the intriguing ideas is that of the multiverse, which posits that our universe is just one bubble in an infinite foam of universes, each with its own space-time setup. In this view, spacetime might be a property that can be created and destroyed endlessly, an eternal dynamic process operating on a larger, perhaps more fundamental level than our familiar universe. Going even deeper, some theories suggest that at the very beginning the concept of spacetime loses meaning altogether. Before the universe's birth, there was no before, no where, no when, just a singularity, a point of infinite density and curvature where our usual rules break down. From this realm, the universe's spacetime unfolded rapidly, perhaps through quantum tunneling or a similar process, giving birth to the cosmos as we know it. What does all this mean for the idea of nothing? It reveals that nothing isn't necessarily empty space or an absence. Instead, it could be a fertile ground of potentiality, a quantum field harboring unmanifested possibilities. From these possibilities, the universe and the spacetime in which it resides can emerge in a burst of creation that blurs the line between nothing and something. In the end, the origin of spacetime remains one of the deepest mysteries and perhaps a paradox of existence. Its creation might ultimately hinge on phenomena beyond our current scientific grasp, residing at the intersection of physics, philosophy, and perhaps something even more profound. Yet, in exploring these questions, we come closer to understanding the wild, wondrous birth of everything, the moment when nothing transformed into the vast, intricate tapestry of space and time that cradles all of existence. Absolutely, quantum fluctuations can indeed create universe-like structures. This idea sits at the fascinating intersection of quantum mechanics and cosmology, challenging our intuitive notions of how reality originates. To grasp this, let's start with what quantum fluctuations actually are. In the quantum realm, the very fabric of empty space, what we might think of as nothing is anything but truly empty. It's a seething, jittering foam of energy, where particle-antiparticle pairs constantly pop in and out of existence in a fleeting dance governed by the uncertainties enshrined in Heisenberg's uncertainty principle. Now, in the context of cosmology, these tiny momentary fluctuations have profound consequences. Imagine the universe's early moments, hot, dense, and filled with quantum fields. During this primordial epoch, these quantum jitters could have been magnified dramatically through a process called cosmic inflation. Inflation posits that the universe expanded exponentially within a fraction of a second after the Big Bang. This rapid stretching acted like a cosmic magnifying glass, stretching microscopic quantum fluctuations to macroscopic scales. What emerges from this process is a universe peppered with regions of varying density, some slightly more dense than others, some less. These tiny differences, initially quantum in origin, served as the seeds for all the large-scale structures we observe today. Galaxies, galaxy clusters, vast cosmic webs. Essentially, the quantum fluctuations provided the initial imperfections in an otherwise smooth beginning, which then grew under the influence of gravity into the complex universe we see now. Think of it like ripples formed when a pebble drops into a pond. Those tiny ripples might seem insignificant, but given enough time and the right conditions, they can amplify into massive waves. In the cosmic setting, the amplified ripples, initially purely quantum disturbances, evolved into the immense galaxy-filled universe. They literally shaped the structure of everything from the smallest dwarf galaxy to the vast expanses of voids separating superclusters. But here's where it gets even more mind-boggling. In some models, these quantum fluctuations can, under certain conditions, give rise to entirely new universe-like regions, pocket universes within a vast multiverse. The idea is that during the inflationary process, some regions might stop inflating and freeze into a universe with its own distinct physical parameters, laws, or constants. Meanwhile, other regions continue inflating, spawning countless other bubble universes. Each of these bubble universes could have different properties, some maybe with different dimensions or force strengths, others with alternate forms of matter and energy. In this way, quantum fluctuations are not just responsible for small-scale structures within our universe. They could be the trigger for entirely separate universes, each born from the chaotic chaos of quantum foam. While such a multiverse remains speculative, no direct observational evidence yet, these ideas are rooted in well-established physics. They push the boundaries of our understanding, suggesting that the universe might not have had a single beginning, but could be one of an infinite number of universes spawned from the endless dance of quantum fluctuations. So, yes, quantum fluctuations aren't just fleeting, microscopic disturbances. They hold the power to assemble the very fabric of reality, to seed the structure of the cosmos, and perhaps even to generate entire new universes out of the seemingly innocuous chaos of quantum foam. This idea challenges and expands our conception of origin, showing that from the unpredictability of quantum events, something as vast and majestic as our universe can emerge, a testament to the bizarre, beautiful and mysterious nature of existence itself. At the heart of understanding the universe's mysterious origins lies the concept of the quantum vacuum. It's a term that sounds deceptively simple, but carries profound implications for how we perceive nothingness itself. Unlike the empty space we might imagine, a dark, silent void, the quantum vacuum is far from empty. It's a seething, frothing backdrop teeming with energy and potential, a kind of quantum playground where particles and antiparticles flicker in and out of existence in fleeting bursts. Imagine the vacuum not as a blank canvas, but as a lively seascape full of shimmering waves of energy that never rest. These fluctuations, called quantum fluctuations, are an outcome of the uncertainty principle, a core feature of quantum mechanics. This principle states that certain pairs of physical properties, like energy and time, cannot be simultaneously measured with perfect precision. So, even in a state of nothing, there's always some residual energy, some restless activity that defies the classical idea of emptiness. Why does this matter? Well, in classical physics, empty space was seen as a void, absolute nothingness where nothing ever happens. But quantum physics paints a different picture. The quantum vacuum isn't static, it's dynamic. The energy inherent in this vacuum can momentarily give rise to particle-antiparticle pairs, which appear out of nowhere, flicker into existence, and then annihilate back into the void in a matter of fractions of a second. It's as if the universe is constantly breaching its own rules, bubbling with spontaneous creation and destruction. This ceaseless activity of the quantum vacuum isn't just a fancy curiosity, it has profound implications for cosmology and the origins of everything we know. For a long time, scientists wondered if these quantum fluctuations could somehow seed the large-scale structure of the universe. Around the time of the Big Bang, it's believed that tiny quantum seedings were stretched to cosmic scales by a process called inflation, an exponential expansion that occurred fractions of a second after the universe's birth. These minuscule quantum jitters grew into galaxies, stars, and planets, shaping the universe into its majestic, sprawling form. Moreover, the quantum vacuum challenges the idea of a universe that began from literal nothing. If the vacuum itself holds energy, then even before the universe existed, there might have been a state of fluctuating energy, a kind of latent potential waiting to give rise to reality. In some theories, the universe could have emerged from these quantum fluctuations, with the vacuum acting as the primordial nursery from which everything blossomed. This shifts the question of origins away from a definite start to a more nuanced understanding. Perhaps the universe is a rare but inevitable bubble in the vast sea of quantum fluctuations. The significance of the quantum vacuum extends beyond explaining the universe's start. It also influences our grasp of fundamental forces and particles. For example, the concept of vacuum energy is closely tied to the cosmological constant, which relates to the accelerated expansion of the universe. The fact that the vacuum itself has energy density suggests that the fabric of space-time isn't static, but is influenced by the quantum properties of the vacuum, leading to fascinating scenarios like the multiverse, where countless universes could spawn from different quantum fluctuations. In essence, the quantum vacuum blurs the line between what we consider nothing and something. It reveals that emptiness isn't void. It's a vibrant, dynamic domain brimming with potential. It reminds us that the origins of the universe may not be a singular event rooted in absolute nothingness, but rather a natural consequence of quantum energy fluctuations, a cosmic dance that has been ongoing long before the universe, as we know it, even came into being. Both loop quantum gravity, LQG, and string theory aim to explain the universe's origin from radically different perspectives, probing the fundamental fabric of reality. LQG suggests that space isn't smooth, but consists of tiny discrete units, akin to pixels or grains of sand. Imagine zooming in endlessly. Instead of smoothness, you'd find a granular structure. These units, called spin networks, form a dynamic woven fabric at the universe's foundation. They are not static but capable of evolution, challenging traditional notions of the Big Bang as a singular point. Instead, LQG proposes a big bounce, where the universe's contraction leads not to a paradoxical infinity, but to a rebound. In this view, before what we see as the beginning, there's a quantum realm where contraction transitions into expansion, avoiding a singularity. The universe may be part of an eternal cycle of oscillations, contractions followed by bounces creating successive universes. This theory suggests the origin isn't a sudden creation from nothing but a phase within a continuous quantum spacetime. String theory approaches origins differently, proposing that fundamental particles are tiny vibrating strings, open or closed, whose vibrational patterns produce particles and forces. This framework requires extra spatial dimensions beyond our familiar three, often compactified and hidden, influencing how strings vibrate and interact. In its more comprehensive version, M theory, these extra dimensions shape the universe's fabric. A key idea in string theory involves brains, multi-dimensional objects that can interact or collide. Our universe might be a three-dimensional brain floating in higher dimensional space. Collisions between such brains could generate energy and matter, effectively acting as a Big Bang. Unlike classical views, which see the Big Bang as the absolute beginning of time and space, string theory suggests the universe emerged from brain interactions within a multiverse, an ever-expanding landscape of multiple universes with varying physical laws. Both theories challenge the classical idea that the universe erupted from literal nothingness. Instead, they propose that the beginning might be a transition or ripple in a more profound structure. LQG envisions the universe's origin as a quantum bounce within a granular evolving spacetime, avoiding the singularity. String theory, meanwhile, posits that our universe could have arisen from the collision or interaction of brains, fundamental objects vibrating in higher dimensions, potentially within a multiversal context. Despite their differences, both theories move us away from simple creation stories based on a singular event. They suggest that the universe's origin is a process, whether a transition, fluctuation, or collision, embedded within an intricate, possibly eternal web of structures. These approaches imply the universe did not emerge from nothing but from a richer, more subtle reality, an underlying realm whose understanding is just beyond current grasp. This perspective opens possibilities for seeing the origin as a phase within a complex infinite fabric, rooted in quantum or multidimensional phenomena. Both theories broaden our view of the cosmos, hinting that the beginning may involve more than a mere moment of inception, but a dynamic evolution within a deeper hidden architecture. By translating these ideas into a framework beyond classical notions, LQG and string theory give us new, potentially harmonious glimpses of the universe's birth. They hint at a reality where the origins are less about an absolute beginning, and more about transitions within a complex quantum or multidimensional landscape. These models, challenging linear narratives, propose that what we see as the start might be but a phase in a broader cosmic cycle, or a result of interactions within an unseen richer structure. Therefore, the initial moments of our universe might be understood as the consequence of processes in an existing ongoing fabric, either quantum or geometric rather than a point of absolute creation. Both theories suggest the universe's origin is part of a deeper, perhaps eternal chain of events governed by the fundamental properties of space, time, and matter. Imagine a point so densely packed with energy and matter that the laws of physics as we know them break down completely. This is what scientists refer to as a singularity in cosmology. It's a concept wrapped in mystery and paradox, an idea that challenges our understanding of space, time, and the very fabric of reality. At its core, a singularity is a place where quantities such as density and curvature become infinite. Think of it as the ultimate breakdown of the usual rules. When we talk about the singularity at the beginning of the universe, we're referring to the moment in the distant past when all the matter, energy, space, and time was squeezed into an infinitely small point, a point where the universe's size was zero and density was infinitely high. This idea emerges from the equations of general relativity, Einstein's masterpiece that describes how gravity bends and shapes space and time. When these equations are applied to the universe's origin, they suggest that if we go back far enough, we approach a moment of infinite density, a singularity. It's like tracing a river back upstream to an endless, waterless point, the source from which everything flows. However, unlike a river's source, which is a tangible, physical point, the singularity is more of a mathematical prediction, an indication that our current theories reach their limits and break down there. Now, why does such a strange concept arise in the first place? If you imagine the universe expanding from a tiny, hot, dense state, what cosmologists call the Big Bang, then at some initial moment the universe's scale shrinking to zero leads us straight into the concept of a singularity. It's as if all space and time were compressed into an infinitely dense point, and from that point, the universe began to expand. But here's where the mysteries deepen. Because in a singularity, quantities like density and gravity become infinite, the usual tools of physics, equations, measurements, even concepts like space and time, cease to make sense. They are rendered meaningless because the math that describes our universe leads to infinities. Many scientists believe that this signals a need for a new, deeper theory, one that combines the principles of quantum mechanics with general relativity. That theory is still elusive, but it's hoped to resolve the paradoxes and provide a clearer picture of what truly happens at that initial moment. It's also worth noting that the notion of a singularity isn't just about the universe's fiery birth. Singularities can also appear inside black holes, regions where gravity is so intense that nothing, not even light, can escape. Inside a black hole, matter is thought to collapse into a singularity, a point of infinite density concealed behind an event horizon, the boundary beyond which escape is impossible. But here lies the philosophical and scientific puzzle. Do these singularities really exist as physical entities, or are they just the signposts telling us that our theories fall apart and need revision? Some physicists believe that quantum effects might smooth out what appears to be a singularity, replacing the infinite with something finite or more comprehensible. In essence, a singularity in cosmology is both a boundary and a horizon, a boundary of our understanding and a horizon for the limits of our physical theories. It represents a tantalizing mystery, the edge of the known universe and the edge of the universe's origin. Whether the universe truly began from an infinite point, or if our current models are simply incomplete, remains one of the most profound questions in science. It beckons us to look beyond the equations, beyond the observable, into the very nature of reality itself. Singularities stand at the edge of our understanding, like cosmic abysses where the known laws of physics break down and space-time itself seems to tear apart. They challenge our notions of nothing and everything, because paradoxically, they represent points where the universe's density becomes infinitely concentrated, outcomes that defy our descriptions of reality. When we consider the universe's origin, we imagine a moment of simplicity, like a point of nothingness before something burst into existence. But science suggests this initial state isn't a tranquil void, it's a singularity. Here, density, temperature, and space-time curvature become infinite, rendering our current equations useless. It's as if the universe was compressed into a point of infinite unknown. Traditional physics, especially Einstein's general theory of relativity, describes large-scale space-time well, but falters at singularities. When density and curvature are infinite, equations yield nonsensical results, similar to dividing by zero. This indicates our understanding is incomplete, or perhaps fundamentally flawed at these extremes. The laws as we know them break down, leaving us gazing into an abyss of ignorance. This breakdown makes singularities perplexing in relation to nothing and everything. If the universe originated from a singularity, an infinitely dense hot point, can we truly say it began from nothing, or was there some pre-existing condition beyond our grasp? In a singularity, the line between nothing and something blurs. Nothing isn't merely empty space, it's a state containing infinite energy and curvature. Anything but emptiness. Moreover, singularities challenge philosophical notions of nothing. Debates continue over whether nothing is a coherent concept. If the universe emerged from a singularity, did it come from absolute nothingness? Or was there an underlying reality before or beyond it? If so, the idea of a true beginning from nothing becomes complicated. The singularity appears as an edge or boundary where space-time ceases to be well defined, a kind of limit rather than an origin. Physics pushes us to reconsider boundary conditions. Quantum mechanics adds indeterminacy and fluctuations at small scales, suggesting even nothing might be teeming with quantum potential. Yet, at a singularity, quantum effects are overwhelmed, and no reliable theory describes what happens. Are singularities just the limits of our current models? Or do they point toward a genuinely new realm, where classical notions of nothing and everything lose meaning altogether? Some scientists argue singularities are artifacts of our equations, not real entities. They propose that a theory of quantum gravity, aiming to unify general relativity with quantum mechanics, might eliminate infinities, replacing singularities with finite structures. Instead of a point of infinite density, perhaps a quantum foam, a bubbling, fluctuating spacetime exists. In such a universe, the transition from nothing to something might be continuous, woven into the quantum fabric rather than a sudden event. The enigma remains. Singularities force us to confront the limits of understanding and ask whether our concepts of nothing and everything are meaningful at these extremes. They hint that reality at its core might be far stranger than current theories suggest. The universe's true origin could lie beyond singularities, where space, time, and causality merge into a deeper, possibly infinitely complex tapestry. In many ways, singularities are both a barrier and a guide, highlighting where our knowledge fails and encouraging us to explore further. Delving into their heart might hold the key to unraveling how everything emerged from what we currently struggle to grasp as nothing. Exploring these infinities may lead us to the ultimate origin, where the boundary between nothing and something dissolves, revealing a more profound understanding of existence. The question of whether the singularity at the universe's beginning is a physical reality or a mathematical artifact has long been debated among physicists, cosmologists, and philosophers. To understand this, it's essential to clarify what a singularity is in Einstein's general relativity. In simple terms, a singularity is a point where certain physical quantities, like density, temperature, and spacetime curvature, become infinite. It's a location where our current understanding of physics breaks down, suggesting a boundary beyond which our models cannot reliably operate. But is this boundary an actual feature of the universe, or merely an indicator of incomplete theories? Some believe the singularity is a real physical entity, a true beginning where space and time emerged from an incredibly hot, dense state. This view stems from the classical Big Bang model, which traces the universe back to a finite moment when all matter and energy were compressed into a point of infinite density. From that point onward, space and time come into existence, supporting the idea that the singularity marks the universe's very birth. However, many argue that the singularity results from the limitations of our current theories. While general relativity describes large-scale structures well, it seems to fail at the singularity. When physicists try to model conditions at these extremes, their equations yield infinities, signaling that the theory is incomplete. Many now see the singularity not as a physical reality, but as a sign that classical physics cannot fully describe the universe's earliest moments, much like a road sign warning of approaching terrain that maps cannot accurately chart. This is where quantum mechanics becomes relevant. While general relativity governs the large-scale structure of space-time, quantum theory excels at describing tiny particles and probabilities. Efforts to unify these frameworks into a quantum gravity theory produce promising results. Candidate theories such as loop quantum gravity and string theory propose that the singularity could be smoothed out, or replaced by a finite, dense yet non-infinite state. For instance, in loop quantum cosmology, the universe's beginning is replaced by a quantum bounce, a transition from a prior contracting phase to the current expanding one. Instead of reaching infinite density, the model predicts a maximum finite density, avoiding the problematic infinities. Similarly, string theory suggests that the singularity may be replaced by a complex multi-dimensional structure that encodes the universe's origins without requiring an actual point of infinite density. These theories imply the singularity might be a mathematical artifact, arising from applying classical physics beyond its valid domain. They suggest that current models are incomplete or approximate, breaking down at extreme conditions. Think of a map that accurately depicts city streets, but fails in the wilderness. When we approach the universe's earliest moments, our classical equations become unreliable. This indicates that a more complete description, perhaps involving quantum gravity, could offer a clearer picture. Philosophically, if the singularity is a mathematical artifact, questions arise. Does the universe truly have a beginning in the classical sense? Or is the idea of a beginning a consequence of the limitations of our models? Perhaps what we interpret as a start is actually a transition from a prior state. We just haven't yet devised the right tools to understand it. The debate hinges on whether the singularity is a real physical phenomenon or a sign of incomplete mathematics. Classical general relativity suggests an infinite density and a boundary, but quantum gravity approaches describe the universe's origins as a smooth, finite process, free of infinities. Without experimental evidence directly probing these earliest moments, the question remains unresolved, inspiring ongoing research and philosophical reflection. This question reminds us of the humility necessary in scientific inquiry. Our theories are powerful but limited, and nature may follow laws beyond our current understanding. The true origin of everything might involve a combination of physics and metaphysics, a story that challenges us to look beyond the singular into the very fabric of reality itself. Ultimately, whether the singularity is a physical reality or a mathematical artifact remains open, fueling both scientific effort and philosophical debate. Word count 604. Imagine a universe where classical physics, with its infinite densities and point-like singularities, begins to unravel like fog dissipating at dawn. Singularities, those elusive points of infinite density and gravity, are the villains in our cosmic story. They appear at black hole centers and mark the universe's beginning, signaling breakdowns of the equations that govern reality. But what if quantum mechanics, with its probabilistic nature and principles of uncertainty, could offer a path beyond these cosmic dead ends? Quantum mechanics introduces probabilities, fluctuations, and uncertainties at tiny scales. Unlike classical physics' deterministic worldview, quantum laws suggest that at extremely small distances, space and time might not be continuous but discrete or quantized. These ideas could smooth out the infinities predicted by classical theories and resolve paradoxes linked to singularities. Take black hole singularities. Classical theories suggest matter, collapsing inward, becomes infinitely dense, crushing all known physics, but quantum effects might prevent this catastrophic collapse. Quantum pressure, from the uncertainty principle and quantum states, could counteract gravity's inward pull. This might lead to a quantum bounce, where instead of collapsing into a point of infinite density, the core reaches a finite, extremely dense state and then rebounds. Essentially, black hole singularities could be replaced by a quantum bridge, possibly creating a cosmic recycling process, with black holes giving birth to new universes. In cosmology, quantum gravity theories like loop quantum gravity, LQG, and string theory explore how quantum principles interact with gravity during high-density phases. Loop quantum gravity posits that space is made of tiny, discrete chunks, much like atoms forming matter. As the universe contracts toward what classical physics calls a singularity, quantum effects dominate, halting collapse. The universe undergoes a bounce, preventing an initial infinite density point. Instead, it transitions from a prior contracting phase into expansion, linking two cosmic epochs and replacing the traditional singularity with a manageable quantum state. String theory offers a different perspective. Here, fundamental building blocks aren't point particles, but tiny vibrating strings. Under extreme densities, these strings stretch, fold, and interact, smoothing out what would otherwise be infinite densities. Some models suggest that the Big Bang isn't an origin point but a big bounce, a transition from a previous universe, bypassing the need for an infinite density singularity. Instead, the universe emerges from a finite extended stringy configuration, folding into our current expanding cosmos. Quantum mechanics also indicates that spacetime itself isn't a smooth continuum. At the tiniest scales, close to the Planck length, spacetime might resemble a frothy quantum foam, a chaotic jumble of fluctuating geometry. These quantum fluctuations could prevent the formation of true singularities, always maintaining some finite, unpredictable quantum state. In this view, the universe's birth isn't a singular point but a fluctuating, dynamic event, a continuous quantum process avoiding the infinities classical physics predicts. These theories represent a shift. They suggest the universe's extreme conditions are governed by quantum laws, which overthrow classical predictions of infinities. By incorporating quantum mechanics into gravity, through quantum gravity, the concept of an infinite singularity diminishes. Instead, what appeared as an ultimate breakdown becomes a transition, a bridge from one state to another. Quantum mechanics challenges our understanding of the infinite and the origin of everything. It implies that singularities are not the final answer, but signs pointing toward a richer, more nuanced reality. The birth of the universe is not a singular event, but a process, an interplay of probabilities, fluctuations, and transitions, making what once seemed singular into a finite, comprehensible phenomenon. The universe's deepest mysteries might not be holes in space-time, but gateways into a broader understanding guided by quantum principles uniting the very small with the infinitely vast. Singularities, points where current physics breaks down, have significant implications for models of creation ex nihilo, the idea of creating from nothing. A singularity is a state where density and curvature become infinite, and our models cannot describe what occurs. Think of it as a cosmic paradox, a point where space and time cease to behave predictably, yet it's often associated with the universe's beginning. But what does this imply for the notion of creation from absolute nothingness? In classical physics, singularities signal that our theories are incomplete. The black hole singularity suggests that gravity and quantum mechanics must be unified. For the universe's origin, the singularity presents both scientific and philosophical challenges. Can the universe emerge from infinite density and zero volume? Or does this indicate our models reach their limits? Models like the Big Bang, which include a singularity at the start, propose that the universe originated from a point of infinite curvature, an initial singularity. This raises profound questions about nothing. If the universe begins as a singularity, does that represent a transition from absolute nothingness, or simply a breakdown of our descriptions? It's as if the models imply that nothing is compressed into an infinitely dense point, not that it vanished. Consequently, the question arises, was there ever true nothing, or is the singularity just a placeholder reflecting our ignorance? This ambiguity has crucial implications. It challenges the idea that the universe emerged from absolute nothingness. Some scientists contend that the singularity isn't truly nothing, but a highly exotic state defying understanding. It's akin to trying to define nothing in a state of extreme density, where our intuitive notions of existence or non-existence no longer apply. Singularities also call into question causality at the universe's origin. If everything emerged from a point where space, time, and laws break down, then cause and effect may lose meaning. The classical concept of causality, central to many creation narratives, may not hold under such conditions. Theorists suggest that causality might break down entirely at these extremes, leaving us in a realm beyond our logical frameworks. Quantum gravity theories like loop quantum gravity and string theory aim to resolve singularities by replacing them with manageable structures, such as quantum bridges or higher dimensional spaces. These theories propose that the singularity could be replaced by a bounce, a transition from a prior contracting universe to our current expansion. If correct, then the idea of a universe originating from a singularity, or from nothing, may be an oversimplification. Instead, the universe's beginning might be part of a larger cyclical process, making the concept of an absolute start obsolete. This shifts focus from a singular moment of creation toward an ongoing or recurring process, challenging traditional notions of creation ex nihilo. The implications extend into philosophical realms. If singularities simply mark our theory's limits, then nothing becomes an even more elusive concept. Are we confronting the boundaries of human understanding, or is nothing beyond scientific and philosophical grasp? If the universe arises not from absolute nothingness, but from a pre-existing continuum, like quantum foam, a prior state, or a higher dimensional structure, then creation ex nihilo is misleading. Perhaps the universe is part of an eternal cycle of creation and destruction, with singularities acting as transient thresholds rather than absolute beginnings. Discussion of singularities pushes us to question the boundary between science and metaphysics. Are they mere technical hurdles, or do they hint at a profound truth that the universe's origin is beyond human comprehension, forever shrouded in mystery? If a singularity marks the limits of current knowledge, future breakthroughs might show that what we see as a beginning was only a transition within a larger, possibly eternal structure, an ongoing emergence, not a one-time event. The universe's origin story may be more complex than a simple beginning, suggesting an underlying process that defies traditional interpretation. As we explore further, we sense that the universe's origin might conceal a more intricate reality, one where the idea of a pristine, absolute nothing before the universe is an illusion. Instead, what appears as a singularity might point toward the interconnectedness of nothing and everything, a puzzle challenging basic notions of existence and creation. The true nature of the universe's beginning remains an open question, at the intersection of science, philosophy, and mystery. It invites us to reconsider what we genuinely mean by nothing and creation, recognizing that our understanding may only be partial. The concept of a singularity as an ultimate origin is fraught with ambiguity, raising as many questions as it answers. Whether singularities are genuine features of reality, or merely signs of our current model's limitations, they compel us to rethink the fundamental nature of the universe's origin. When we look back to the moments before the Big Bang, our understanding becomes highly speculative, as physics pushes against what's observable and known. Several theories aim to uncover conditions before this event. One compelling idea is the cyclic universe. This theory suggests that our universe is part of an eternal cycle of rebirths, big bangs followed by big crunches. The universe continuously expands, contracts, and then expands again in an infinite loop. Each cycle begins with a new explosion, possibly echoing a previous universe, implying that the perceived beginning might be just one phase in an ongoing cosmic rhythm. Though mechanics are debated, this idea challenges the notion of a singular beginning, indicating a universe that existed long before the Big Bang. The Epyrotic University offers another perspective. Rooted in brain-world cosmology, it envisions our universe as a three-dimensional brain floating in a higher dimensional space. Imagine this brain gently colliding with another, generating the energy and matter we see as the Big Bang. Instead of originating from nothing, the universe emerges from interactions of higher dimensional structures that existed before the collision. This scenario posits the initial event as the result of deeper, pre-existing conditions, rather than a true starting point. Quantum cosmology explores the universe's origin through quantum mechanics. Here, the idea is that the universe can be described by a quantum state, full of probabilities, superpositions, and indeterminate states, rather than a classical event. The Hartle-Hawking no-boundary proposal suggests the universe is akin to a finite boundaryless surface similar to a sphere. Near what we call the origin, time becomes fuzzy, and the universe transitions smoothly from a quantum realm where traditional notions of space and time no longer apply. This implies that asking what came before the Big Bang might be nonsensical, as the fabric of reality at such scales is fundamentally different. Loop quantum gravity offers another approach. It seeks to unify Einstein's general relativity with quantum mechanics by describing space as composed of tiny, discrete chunks. In this framework, the Big Bang is replaced by a big bounce, a transition from a contracting universe into the expanding one we observe today. Instead of a singularity where physics collapses, the universe reaches a minimal, finite size and then bounces back. The universe before this bounce, during its contraction, raises questions about what that pre-expansion cosmos looked like. String theory also provides insights. Its core idea is that fundamental reality constituents are one-dimensional strings vibrating at specific frequencies. String theory suggests a vast multiverse, where numerous universes emerge from a larger cosmic landscape. Some models propose our universe originated from higher dimensional membranes, or brains, interacting to create new universes or phases. Instead of a singular event out of nothing, the universe's origin might be a chapter in a sprawling multiversal tapestry, woven across higher dimensions and ongoing cosmic processes. These theories all grapple with the limits of current knowledge but share a core idea. The universe's beginning, especially what predates the Big Bang, is connected to realms where classical understanding fails and quantum, multidimensional or cyclic principles dominate. Their pursuit continues to inspire physicists and philosophers alike, forcing us to rethink what nothing means, and whether the universe's origin is truly a starting point or part of an ongoing, perhaps infinite cosmic story. The Epyrotic model offers a fascinating alternative to the traditional Big Bang theory, proposing that our universe's origins stem not from a sudden explosion, but from a cosmic collision, a kind of celestial dance that sets the stage for everything we observe today. The name, derived from the Greek ekpyrosis, meaning conflagration or out of fire, hints at a universe born from energetic rebirth, not from nothing in the classical sense. Imagine the universe as part of a higher dimensional space, a realm beyond our familiar 3 dimensions of space and 1 of time. Within this multidimensional stage, objects called brains, short for membranes, can coexist, brush past, or collide. These brains are fundamental in string theory, which explores the universe's deepest fabric. In the Epyrotic model, our universe resides on one such brain floating in higher dimensional space. This existence isn't static. The story unfolds when this brain, the cosmic home, starts moving through this space toward another brain. Over time, driven by underlying physics, these brains drift closer, akin to sheets of paper gently drawn toward each other. Eventually they collide. Unlike the violent explosion of classical Big Bang models, this collision is smooth and gentle, a subtle contact that releases immense energy. The impact creates a hot, dense state that ignites matter and radiation, giving rise to what we recognize as our universe. This event acts as a cosmic reset, seeding the universe's expansion, structure formation, and evolution. The Epyrotic model is cyclic. It proposes a universe undergoing endless cycles of collisions and rebirths. After each collision, the universe expands, cools, and develops complexity. Over eons, the brains drift apart again, only to be pulled together for another collision, a process possibly spanning billions of years. This cyclicity suggests an eternal cosmos, not one with a definitive beginning in nothingness, but a universe in an infinite rhythm of rebirth. One appealing aspect is its ability to resolve questions traditional physics struggles with. For instance, it naturally explains the universe's observed flatness and uniformity without requiring an initial inflationary phase. The Epyrotic process smooths out irregularities, setting initial conditions for large-scale structure formation. It also addresses the problematic singularity, the infinite density point, by describing the collision as a finite, well-understood event within higher dimensional space, avoiding the paradoxes of a classical Big Bang singularity. Another intriguing feature is its potential to generate the tiny density fluctuations that grow into galaxies and galaxy clusters. These primordial ripples arise naturally from the brain collision dynamics, offering a compatible origin for the universe's large-scale structure without relying on rapid inflation. However, the model faces challenges. It heavily depends on the existence of extra dimensions and brains, concepts still highly theoretical and not empirically confirmed. It's a bold hypothesis that pushes current experimental boundaries. Still, it offers a fresh perspective, one suggesting the universe's story might be less about an abrupt beginning from nothing and more about a long cyclic history woven into higher dimensional fabric. In this way, the Epyrotic model reimagines cosmic origins. Instead of a sudden leap from nothing, it envisions a universe born from the collision of multidimensional membranes, a cosmic rebirth within a vast, potentially eternal multiverse dance. It blurs the distinction between creation and continuity, implying that perhaps the universe's beginning is not a final event, but part of an ongoing, infinite cosmic story spanning dimensions beyond our immediate perception. Imagine the universe as a tiny bubble floating within an endless cosmic ocean, filled with countless other bubbles, each representing a universe. This is a core idea of multiverse theories, viewing our universe as just one of potentially infinite universes, part of a multi-layered reality. But how does this explain our universe's origin? And what does it mean when we say our universe might be just one piece of a much larger puzzle? Multiverse theories propose that what we perceive as the universe isn't the only one. Instead, there are multiple, possibly infinite universes, each with its own physical laws, constants, and initial conditions. Some models come from quantum mechanics mathematics, others from cosmological theories about space and time's beginnings. Take cosmic inflation. This idea suggests that shortly after the Big Bang, the universe expanded exponentially. During this rapid stretch, tiny quantum fluctuations in spacetime could have led to the formation of pocket universes, regions that stopped inflating and became self-contained universes. Think of bubbles forming in boiling water. Each bubble inflates, then pops off, drifting away. Multiply this process over vast space, and you see how multiple universes could emerge from a single event. This cosmological multiverse isn't just about pockets within our universe. Some theories suggest entirely separate universes existing in different higher dimensional realms, spaces beyond our three spatial dimensions and time. These extra dimensions form a sort of superstructure, where each universe exists in its own region, unaware of others. String theory, for example, proposes that our universe might be a tiny membrane, a brain in a higher dimensional space. Other brains could host their own universes, separated by imperceptible distances. Quantum mechanics adds another perspective. The many worlds interpretation claims every quantum event spawns a new universe. Each possible outcome of measurement unfolds separately. Every decision, every chance encounter creates a new universe. It's like a vast library where all possible histories exist simultaneously. Our universe is just one branch, where a specific sequence of quantum events led to today's universe. How do these theories relate to the universe's origin from nothing? In some models, nothing isn't empty void but a quantum vacuum full of potentialities. Tiny fluctuations periodically appear and vanish. Under certain conditions, a universe could spontaneously nucleate from this quantum foam. Similar to bubbles forming in boiling water seemingly out of nowhere, our universe might have arisen from a quantum fluctuation, an inherent possibility within the universe's quantum fabric. Multiverse theories challenge our understanding of existence. They suggest that the question, where did everything come from, may not have a single answer but many. Our universe might be just a ripple in an infinite ocean of others, each with its own story, rules, and origins. If true, the story of our universe's beginning isn't confined to a single moment, but woven into a vast multidimensional fabric, an intricate dance of quantum potentials, cosmic bubbles, and higher dimensional realms within the boundless multiverse. These ideas stretch our imagination and reshape notions of creation. They imply our universe might be just one of countless others, with origins rooted in quantum fluctuations, cosmic inflation, and higher dimensional spaces. Multiverse models suggest that everything we know is part of an immense, interconnected tapestry, where countless universes continuously form, evolve, and fade away across staggering scales. Whether or not we can directly observe this multiverse, it offers an expansive framework for understanding how our universe might have come into existence, as one piece in an infinite cosmic mosaic. String theory offers a fascinating, if complex, perspective on the origins of the universe, one that diverges sharply from traditional ideas of a single, definitive beginning. Instead of envisioning the universe bursting into existence from a point of absolute nothing, string theory proposes that what we perceive as the universe's inception might be a manifestation of deeper, multi-dimensional processes rooted in the fundamental nature of reality itself. To understand this, imagine that the fundamental building blocks of everything are not point particles, as in classical physics, but tiny, vibrating strings. These strings, so minuscule that they dance at scales billions of times smaller than an atom, can vibrate in numerous ways. Each vibrational pattern corresponds to a different particle, giving rise to the diverse array of matter and forces we observe. This elegant idea ties the fabric of the universe directly to the vibrations of these strings, weaving the fabric of space, time, and matter into a unified tapestry. But how does this relate to the start of everything? Well, string theory suggests that the universe's inception might not have been an explosion from nothing but a transition in a higher dimensional space. In classical cosmology, the Big Bang is often depicted as a singularity, a point where densities and temperatures become infinitely large, and the laws of physics break down. But within string theory, this singularity might be an artifact of the limitations of our previous models. Instead, what appears as a singular point could be a smooth transition within a richer, multi-layered structure. One way to picture this is through the concept of brains, multi-dimensional objects predicted by string theory. Our universe could be a three-dimensional brain floating in a higher dimensional space. Imagine two such brains drifting closer together within this vast multi-dimensional arena. Their collision could trigger a tremor that ignites the formation of our universe, akin to how ripples on a pond emanate from a stone splash. In this scenario, the beginning isn't a bang originating from absolute nothing, but a gentle, yet profound collision, an event rooted in the dynamics of higher dimensions. Furthermore, string theory paints a picture where the early universe might have experienced a bounce rather than a singular beginning. Instead of jumping from nothing to something in a single, uncaused instant, the universe could undergo cycles of contraction and expansion. Each bounce resets the conditions, but the process is governed by the vibrations and interactions of strings within the higher dimensional space. This cyclic model implies that the inception, or the Big Bang, might be just one phase in an endless rhythm, a passage from one state of cosmic vibrancy to another. Another intriguing aspect is the possibility that our universe is just one of countless others, each associated with different vibrational states of strings or different configurations of extra dimensions. These other universes might exist within a vast multiverse, a meadow of bubbles, each with its own physical laws and constants. From this perspective, the inception of our universe might be akin to a bubble nucleating within a cosmic foam, a process that string theory provides a framework for understanding without invoking absolute creation from nothing. All of these ideas point toward a universe that emerges from a much deeper, more complex structure than what classical physics describes. String theory hints that what we perceive as the beginning is part of a grander, multi-dimensional dance, where vibrations, brains, and the fabric of spacetime itself conflate into a seamless narrative. The inception point may not be a single, isolated event rooted in nothingness, but a dynamic unfolding within a multi-layered universe, one that is still, in many ways, beyond our complete understanding. Instead of seeking the moment when existence began, we find ourselves on a journey exploring the symphony of strings vibrating into the cosmic story we are part of, a story that perhaps has no true beginning, but rather flows eternally in endless variations. When contemplating models that reach back before the Big Bang, the question of observable consequences becomes one of the most tantalizing puzzles in modern cosmology. If these theories, like the cyclic universe, multiverse hypotheses, or quantum bounce models, are correct, is there any signature, any whisper from the distant past that we can detect today? Could the faint echoes of a pre-Big Bang epoch have left imprints on the universe that we can observe with our telescopes and detectors? One promising avenue lies in the cosmic microwave background radiation, the faint glow that permeates all of space. This radiation is a relic from the universe's earliest moments, once hot and dense enough to be opaque. While traditional models of inflation neatly explain the uniformity and slight anisotropies observed, some pre-Big Bang scenarios predict subtle deviations or anomalies within the CMB. For instance, certain cyclic models posit that if the universe underwent a series of contractions and expansions, small irregularities from prior cycles might survive or influence the pattern of fluctuations we see today. Perhaps deep within the polarization patterns or in the distribution of temperature anisotropies, there are clues, anomalies that deviate from the expected inflationary predictions, that hint at phenomena predating the Big Bang. Beyond the CMB, gravitational waves present another promising window. These ripples in spacetime could carry signatures from epochs before the universe's hot Big Bang phase. Specific models predict a background of primordial gravitational waves that differ in amplitude or frequency spectrum, depending on what processes occurred in the pre-Big Bang universe. For example, a cosmological bounce, a transition from contraction to expansion, could generate a unique gravitational wave signal. Such waves would be incredibly faint, but upcoming detectors like space-based interferometers or advanced ground-based observatories might be sensitive enough in the future to pick up these primordial signals. Detecting such a background and analysing its spectrum would allow scientists to distinguish whether the universe's earliest moments align more with a sudden singularity or a smooth transition from a previous state. Another potential observable involves large-scale structures, galaxies, clusters, and voids woven into the fabric of the cosmos. If pre-Big Bang physics influenced their distribution, patterns or alignments might emerge that can't be easily explained by standard inflationary perturbations. For example, some have suggested that anomalies like the so-called cold spot in the CMB or other hemispherical asymmetries could be relics of processes that occurred before the universe's hot, dense phase. These patterns might serve as archaeological evidence, revealing a layered history stretching beyond the conventional cosmological timeline. Yet, despite these promising channels, challenges abound. The signals predicted by pre-Big Bang models tend to be incredibly subtle, often lying beneath the noise threshold of current instruments. Many of the hypothesized signatures are indistinguishable from, or masked by, cosmic variance, astrophysical foregrounds, or limitations of measurement precision. Moreover, different models can produce similar signatures, making it difficult to unambiguously identify a pre-Big Bang origin. Furthermore, the very nature of these models demands a framework that extends beyond classical physics. Quantum gravity remains elusive and poorly constrained. Without a complete and accepted theory of quantum gravity, translating these ideas into precise testable predictions remains a formidable hurdle. Despite these challenges, the quest continues. As observational technology advances, as experiments become more sensitive, and as our understanding deepens, the possibility of detecting signatures from before the Big Bang persists. It's a profound pursuit, searching for the faintest echoes of eternity's first whisper, trying to unveil the conditions that laid the groundwork for everything we know. If we find such traces, it could revolutionize our understanding of existence itself, turning the mystery of how everything started from absolute nothing into a story that we can finally begin to read. The question of how the laws of physics came into existence is one of the most profound mysteries in understanding our universe's origins. When we look back to the earliest moments, closer than the Big Bang, we find a universe so dense and hot that space and time seem to dissolve into a singularity, a point of infinite density and curvature. But within this realm, a perplexing question arises. If the universe began with these laws, where did they originate? Were they always present, waiting to be discovered? Or did they come into being as part of the universe's unfolding story? To unravel this, we must recognize that the laws of physics aren't like rules imposed from outside the universe. Instead, they seem woven into the fabric of reality itself, rules that appear consistent and universal, governing particles, forces, energy, and matter. Yet, at the earliest moments, physics begins to blur. Quantum mechanics describes the subatomic world with probabilities and uncertainties, while general relativity depicts gravity as spacetime curvature. These frameworks are successful within their domains, but at the initial state, where densities and energies become infinite, they clash in ways that challenge understanding. Some scientists suggest that the laws of physics may not be fixed laws, but emergent phenomena arising from more fundamental principles we're still trying to comprehend. Think of physics as an evolving story, where simple symmetries generate particles, forces, and structures observed today. In this view, what we call physical laws could be akin to patterns emerging from underlying chaos, rules dependent on initial conditions and perhaps changing over long timescales. Another perspective considers that the laws may have been set in the universe's very fabric at its birth, if such a birth exists. In models involving string theory or the multiverse, physical parameters emerge from a landscape of possibilities. Different regions of a vast multiverse might have different laws, with our universe just one bubble with laws suited to its conditions. Here, laws are environmental properties, resulting from cosmic selection as universes form and evolve. Quantum cosmology offers a different view. The universe's origin was a quantum event, a cosmic fluctuation, where the laws of physics materialized alongside the universe. In this framework, these laws aren't fundamental preconditions, but phenomena emerging from the universe's quantum state. Time, space, and the laws become intertwined in a delicate quantum dance where cause and effect blur at the universe's inception. Some theories push even further, suggesting that physical laws are not fixed but are part of a dynamic process, evolving or metamorphosing over cosmic time. If so, their origins are chapters in an ongoing story of cosmic change, requiring us to explore beyond conventional science into realms where the concept of law becomes fluid and complex. Ultimately, the question remains open. It occupies a frontier where physics, philosophy, and metaphysics converge. Did the laws pre-exist, simply setting the stage for the universe's unfolding? Or did they arise spontaneously at the universe's birth? Or do they emerge from deeper principles beyond our current understanding? As we probe further, perhaps we will peel back the veil that shrouds this mystery, revealing the extraordinary story of how the universe's governing rules came to be. The question of why physical constants are fine-tuned for life has puzzled scientists and thinkers for centuries. It's as if the universe was crafted with delicate precision, designed, or perhaps coincidentally set up to make life possible. To understand this, we need to look at what these constants are and why their exact values matter so profoundly. Constants like the speed of light, the gravitational constant, the electromagnetic force, and the mass of fundamental particles aren't arbitrary numbers. They govern the behavior of everything in the universe. If any of these were slightly different, the universe as we know it might never have formed. For example, a slightly weaker or stronger electromagnetic force could prevent atoms from forming or holding together. Without stable atoms, molecules, planets, or life, the universe would be silent and barren. Similarly, a different gravitational constant might mean stars don't ignite or sustain nuclear fusion, resulting in no heat, no light, and no life as we understand it. This remarkable precision suggests two possibilities. Either the universe was intentionally fine-tuned, or it resulted from some cosmic accident. The idea of fine-tuning sparks curiosity, leading many to wonder if these constants are set that way due to a deeper reason, perhaps a purpose or a design. Others argue that apparent fine-tuning might be an illusion, caused by the universe being one of an almost infinite number of universes in a multiverse, where every possible set of constants exists somewhere. In a multiverse scenario, most universes would have constants that render them inhospitable, collapsing or expanding too quickly for structures to form. Only a tiny subset would have parameters finely tuned enough for complex life. Our universe might just be one of those rare lucky ones. It's a kind of cosmic lottery. Universes with the right parameters win the chance to host life. This shifts the question from why are the constants fine-tuned to, given the multiverse, isn't it unsurprising ours supports life? Some physicists explore the idea that these constants aren't arbitrary, but linked through deep physical laws or symmetries yet to be discovered. Maybe they aren't constants at all, but variables connected through an elegant underlying theory, like a grand unified theory, that explains why their values are what they are. In this case, the universe's fine-tuning might be inevitable, a consequence of fundamental principles governing reality. If such a theory exists, it could bridge physics and metaphysics, transforming what seems like cosmic coincidence into the natural result of deeper laws. What if the universe's constants aren't fixed? Some theories propose they might vary across space and time. If so, then perhaps the universe has experienced different phases where conditions were less suitable for life. We might just be fortunate to exist where parameters align perfectly. This introduces even more possibilities. A cosmos where properties are dynamic rather than static, with regions or moments more hospitable than others. As science pushes further into the fabric of reality, the question of fine-tuning intertwines with existential wonder. It urges us to consider whether the universe's precise values reflect a purposeful design, a cosmic accident, or the consequence of a vast multiverse where randomness and necessity coexist. Each answer reveals new mysteries, hinting that our universe's life-friendly nature might be only the beginning of a much larger, possibly incomprehensible picture of existence. The phenomenon of fine-tuning continues to challenge and inspire, driving us to explore the fundamental nature of reality and our place within it. Imagine a cosmos where the fabric of reality dances to a different tune, where the constants and laws governing our universe are not fixed, but fluid, adaptable, and malleable. This idea suggests that, in some other universe, the fundamental laws of nature could differ from what we experience on Earth. It stretches our imagination and challenges the notion of certainty in the universe's design. Our universe follows precise physical laws: gravity, electromagnetism, the nuclear strong and weak forces that operate consistently across space and time. These laws give the universe predictability and enable scientific understanding. But what if this isn't the only way reality can be structured? What if, in some other universe, part of a multiverse, the rules of physics are altered or don't exist as we understand? This idea comes from theoretical physics and cosmology, where the multiverse hypothesis suggests an ensemble of universes, each with its own set of laws, constants, and initial conditions. Some might have different force strengths. In one, gravity could be weaker, preventing star or planet formation. In another, it might be so strong that matter collapses instantly after creation. Electromagnetic force variations could make chemistry, if it exists at all, completely different and largely unrecognizable. Even more mind-bending is the idea that the number of spatial dimensions could differ. In our universe, space has 3 dimensions, but perhaps in a neighboring universe there are 4, 5, or 10. How would the laws of physics manifest there? Would gravity behave similarly or take a different mathematical form? What about particles and fields? Could they be entirely new entities? Might the concept of particles be meaningless in some universes? Some theories, like string theory, posit higher dimensions and suggest different universes emerge from various ways of compactifying extra dimensions. In some, the constants of nature, such as the electron's mass or the nuclear force's strength, could vary wildly. Such universes might be inhospitable, barren, and lifeless, or teeming with phenomena completely alien to ours. Why would the laws differ across universes? Many propose these laws emerge from the multiverse's structure itself, like different settings on a cosmic keyboard. If the multiverse forms through cosmic inflation, an exponential expansion post-Big Bang, each bubble could have different initial conditions, leading to different physical laws. The mechanisms behind these universes might be inherently random or probabilistic, creating a vast diversity of realities. What does this mean for us? It compels us to reconsider what we deem fundamental. If the laws of physics vary across realities, then ours might simply be one where constants align perfectly, enabling life, complexity, and consciousness to flourish. Other universes could be sterile, chaotic, or unrecognizable. This idea, that the laws of nature could vary elsewhere, offers a glimpse into an infinitely varied multiverse, filled with countless possibilities. It reminds us that what we see as absolute might just be one of many different settings, each with its own rules. Exploring this expands science and philosophy, urging us to ponder whether there is a deeper underlying order, or if everything we know is just one chapter in an unimaginably vast multiversal story, written in different dialects of reality's fundamental laws. In this vast multiversal landscape, universes with different physical constants, force strengths, and spacetime dimensions could exist, each providing a unique set of rules shaping their reality. Some may be inhospitable or chaotic, others might host entirely different forms of matter, energy, and life. The mechanisms behind their emergence remain speculative, yet they challenge our understanding of what is necessary for a universe to exist. If the laws of nature are not fixed, then our universe might be just one improbable configuration among many. This concept pushes us to reconsider the nature of reality itself and our place within it, suggesting that our universe's finely tuned constants may simply be one outcome in an enormous cosmic lottery. The multiverse hypothesis expands our perspective, hinting at a vast, diverse, and perhaps infinite cosmos, one where the fundamental rules are as varied as the stars and dimensions that compose it. The Anthropic principle is a captivating idea that prompts discussions among physicists, cosmologists, philosophers, and curious laypeople about the universe's design. When considering the constants of nature, those fundamental values shaping reality, it's natural to wonder whether their precise figures are mere coincidences or if something deeper is at work. The Anthropic principle provides a lens through which to interpret these constants, suggesting that perhaps the universe appears finely tuned for life because if it weren't, we wouldn't be here to question it. Think of the cosmological constants, like the gravitational or cosmological constant, numbers so exact that even tiny deviations could drastically alter the universe's structure or make it inhospitable. Different values might prevent star formation, galaxy development, or the existence of life as we know it. This level of precision feels almost intentional, like a universe with extraordinary care. But is this because of deliberate design, or is there another explanation? This is where the Anthropic principle comes into play. There are two main versions, weak and strong. The weak Anthropic principle states, we observe these specific constants because only those allow for observers like us. In other words, out of potentially countless universes or configurations, only some can support life. We happen to be in one of those rare, finely tuned universes because if we weren't, we couldn't be here to observe it. This perspective is more of a cosmic concession, recognizing that our existence limits what we can observe, but not implying intentional design. The strong Anthropic principle suggests something more. It proposes that the universe must have properties that support life, almost as if it's compelled or predisposed to produce conscious beings. Some interpret this as implying that the universe knows to support life, or that multiple universes with different constants exist, with ours being the one suitable for life. This idea dovetails with multiverse theories, collections of possibly infinite universes, each with different laws or constants. If true, the Anthropic principle explains why we observe the particular values we do, because we can only exist in a universe where conditions permit life. However, the Anthropic principle doesn't clarify why the constants have their specific values. It frames our understanding within the context of our existence. It's more a philosophical perspective than a scientific explanation. Yet, it has profound implications. It shifts the inquiry from why is the universe so finely tuned, to given that we exist, what must be true about the universe? This subtle reversal deepens the discussion. Critics argue that the Anthropic principle can seem like a cop-out, suggesting we may never fully understand why the universe's constants are as they are. They worry it risks becoming tautological. A universe's constants incompatible with life simply wouldn't be observed or questioned. On the other hand, supporters see it as a useful heuristic, a practical tool when direct evidence is lacking for why constants have their values. From a deeper view, the Anthropic principle blurs the line between physics and philosophy, forcing us to confront questions about existence, purpose, and the limits of scientific inquiry. Are we mere product of cosmic luck with constants shaped by the multiverse or a cosmic landscape? Or is there some underlying reason, an overarching order that we've yet to grasp? As our knowledge of early universe physics, quantum mechanics, and the multiverse expands, the Anthropic principle is likely to remain central to interpreting the universe's fine-tuned constants. It reminds us that, in the vast cosmic lottery, we're part of a specific fragile outcome. Whether this delicacy hints at divine design, necessity, or chance, the question of why the constants are just right continues to ignite our curiosity. Deepening our fascination with the cosmos and our place within it, the emergence of laws, fundamental rules governing the universe, raises intriguing questions when contemplating nothing. If the universe begins from absolute nothingness, devoid of matter, energy, space, and time, where do these laws originate? Do they pre-exist, or do they somehow emerge from chaos? This question lies at the heart of understanding reality. In a universe from nothing, laws, sets of principles dictating behavior, become less straightforward. Traditionally, laws are seen as eternal, intrinsic, and unchanging features. But if the universe emerges from nothing, can laws be embedded in that initial state? Or do they come into existence along with space and time, or even shape them? Some physicists consider laws not strictly necessary for existence, or view them as emergent rather than fundamental. Imagine a quantum fluctuation, a brief blip in quantum fields, causing a tiny region to pop into existence. Initially, chaos reigns, unstructured energy and particles, and from this chaos, patterns and regularities emerge. Over time, these structures formalize into physical laws, rules that predict and describe behavior. This suggests laws are akin to patterns stemming from complex interactions, not pre-existing templates. In a universe from nothing, nothing might not be empty, but a state of potential filled with quantum possibilities. These possibilities don't follow classical rules but are governed by quantum mechanics. From this quantum soup, stable configurations become more likely, leading to nascent laws that crystallize into the principles of physics. Another idea is that laws are tied to quantum reality itself. Some theories posit laws as manifestations of underlying quantum conditions, initial states or constraints shaping what can happen. In this view, laws aren't timeless artifacts but emergent properties that develop as the universe evolves, influenced by initial conditions, boundary constraints, and quantum fluctuations. This makes the origin of laws deeply connected to initial conditions. If the universe starts from nothing, a state lacking preferred directions or properties, the laws we observe today must have arisen from that primordial state, perhaps through symmetry breaking or phase transitions. Just as cooling water forms ice crystals with regular patterns, the universe might have cooled into states where specific laws dominate, shaping subsequent behavior. Some perspectives suggest laws aren't fixed, but are statistically favored tendencies. When the universe is small and dense, certain behaviors become more probable, making some laws appear more prominent. As the universe expands and evolves, these tendencies stabilize, giving the impression of unchanging laws. In this view, lawfulness emerges from persistent statistical patterns, order arising from an initially unordered, lawless state. The concept of laws may blur the line between fundamental and emergent. Instead of pre-existing blueprints, laws could be self-organizing principles resulting from the universe's transition from potentiality to actuality. From a quantum foam of possibilities, nothing, these principles emerge, guiding the universe's development and leading to the complexity observed. Contemplating this reveals that reality's fabric might not be woven with immutable laws from the start, but that these laws are woven over time, shaped by quantum processes, symmetry breaking, and cosmic evolution. They are not external constraints imposed on chaos, but are features that emerge naturally as the universe unfolds from pure potential into structured phenomena. The universe's birth from nothing becomes a story of order, law, and structure, arising spontaneously from emptiness, a poetic dance from nothing into everything. Exploring how scientific explanations intersect with theological creation stories reveals a space where boundaries of understanding often blur, and the quest for truth takes many forms. Humanity has long sought to answer the profound question, how did everything start? Through scientific inquiry and stories rooted in faith, tradition, and spiritual insight. These explanations reflect different ways of knowing and perspectives on existence, influenced by culture, philosophy, and divine experience. Many religious traditions present creation stories as foundational narratives, framing the universe as the deliberate act of a divine creator. These stories often describe a purposeful beginning, God speaking the world into existence out of divine will or love. They embed humans within a divine plan, providing moral and existential meaning. For instance, the Genesis account in the Bible depicts the universe emerging over 6 days through divine acts emphasizing order, intention, and sovereignty. Similarly, in Hindu tradition, the universe arises cyclically through Shiva's dance or Brahma's cosmic emanation, symbolizing eternal processes beyond time. Conversely, scientific explanations based on observation and empirical evidence approach the universe's origin as a process understandable via models like the Big Bang, quantum fluctuations, or multiverse hypotheses. These focus on mechanisms that drove the universe's emergence without denying the possible existence of a divine creator. For example, the Big Bang proposes a cosmic event from an extremely hot, dense state about 13.8 billion years ago, marking the beginning of space, time, and matter. The intersection becomes fascinating when perspectives challenge, complement, or coexist with each other. Some view science as describing the how, the physical laws and processes shaping the universe, while seeing religious stories as addressing the why, the purpose and meaning behind it all. This division allows for a non-conflicting relationship. Science explains the mechanics, religion provides the narrative of significance. Many find comfort in the idea that faith and science answer different questions, like two sides of a coin. However, literal interpretations of religious texts can conflict with scientific evidence. For some, a young Earth, or a 6-day creation, conflicts with geological and cosmological timescales. This tension has prompted debates over interpretive flexibility, whether these stories are literal histories or allegories for deeper truths. Prominent theologians and scientists argue for poetic or non-literal readings, viewing scripture as expressing universal truth through symbolic language compatible with science. The questions of fine-tuning and existential purpose also foster dialogue. The universe's precise physical constants seem improbably calibrated to support life, leading some to infer an intelligent designer. Others view these conditions as resulting from natural processes within a multiverse, a vast ensemble of universes with varying constants, where ours is simply one suitable for life. A rich mosaic of views emerges. Some merge science and faith into harmonious narratives, others see them as distinct but mutually enriching. Both challenge us to reflect on the universe's infinite complexity, whether studying cosmic phenomena or contemplating divine acts. Both inspire awe, wonder, and humility. When viewed at their intersection, it becomes less about choosing between science and theology, and more about understanding the profound mystery connecting all efforts to comprehend existence. Ultimately, the most beautiful aspect of this interplay is that both scientific explanations and theological stories serve as pathways, different routes toward the same horizon of curiosity, meaning, and wonder. They invite us to be explorers in a universe vast beyond measure, seeking understanding not only in the laws governing the stars, but also in mysteries that stir the soul. In the dance between science and faith, Both serve as vital tools in humanity's ongoing quest to understand our origins, purpose, and place in the cosmos. The question of whether science and religion can reconcile in explaining the origin of everything from nothing touches on deep human curiosity and belief. On the surface, they seem worlds apart. Science grounded in empirical evidence, testable hypotheses, and a quest for understanding, while religion relies on divine purpose, sacred texts, and spiritual truths beyond observation. Yet, beneath this divide, there's a potential for dialogue, a way to bridge perspectives that might enrich our comprehension of the universe's origins. Recent decades have seen science uncover remarkable insights into the earliest moments of existence. The Big Bang Theory suggests the universe expanded from an incredibly hot, dense state, a point where space and time seem to begin. Quantum fluctuations hint at a universe that could originate from a nothing teeming with potentialities, governed by the strange rules of quantum mechanics. Cosmologists explore models like cosmic inflation and multiverses, which challenge understanding about initial conditions and the nature of nothing. These theories imply that what we call nothing is actually a quantum foam, a bubbling landscape of potentiality rather than an absolute void. Religion, on the other hand, often posits a divine act, the prime mover or creator, bringing everything into existence from nothing through divine will. In many traditions, this act of creation reflects divine sovereignty, intention, and purpose, framing the universe as a manifestation of a higher power's plan. The idea that all emerge through divine speech or command resonates across cultures, suggesting that creation is a conscious act of divine power. The apparent conflict arises because these explanations seem to speak past each other, one about physical processes and natural laws, the other about divine intent and purpose. But many philosophers and theologians suggest the divide isn't necessarily one of incompatible truths, but different perspectives illuminating different aspects of the same mystery. Some propose that scientific descriptions of the universe's beginning could reveal mechanisms through which divine acts manifest, natural processes part of a divine order. Others argue science and religion ask different questions. Science explains how the universe came into being, focusing on causality and physical laws. Religion seeks to understand why, the purpose behind existence itself. From this view, they can coexist as complementary rather than conflicting narratives. Science marvels at mechanisms, quantum fields, space-time fabric, while religion emphasizes the meaning behind those mechanisms, the spiritual significance of existence. Reconciliation isn't about reducing one to the other, nor forcing harmony. It involves recognizing that both can be parts of a larger understanding. For some, science inspires awe at universe's complexity and delicate balance, blending well with spiritual wonder. Conversely, faith provides a framework to contemplate purpose and meaning behind scientific discoveries, the idea that the universe's origin might reflect divine intention or creative power. Open dialogue fosters unity, acknowledging that questions about existence, origin, and purpose are among humanity's most profound. While science may not address divine purpose directly, it can deepen appreciation for the cosmos' intricate beauty, often reflected in spiritual worldviews. Similarly, faith can motivate scientists to look beyond data toward the mystery at the core of curiosity. Perhaps the most compelling reconciliation recognizes that both perspectives, each profound, invite us to a deeper encounter with the mystery of existence. Whether viewed through empirical discovery or spiritual insight, seeking to understand the origin of everything from nothing remains a vital human journey, a dialogue that calls for humility, wonder, and awe. This ongoing engagement underscores that science and religion, rather than opposing, can work together to enrich our understanding of the universe's origins. Ultimately, both pathways, scientific and spiritual, offer ways to explore the profound mystery of existence, reminding us that the pursuit of knowledge is an endless journey of discovery, reflection, and reverence. The question of divine action versus natural processes has long been at the crossroads of philosophy, theology, and science. To explore how each might have played a role, or continue to influence our understanding, requires peeling back layers of assumptions, beliefs, and scientific inquiry. Some thinkers propose that the universe's origin can be fully explained by natural processes, complex, finely tuned, but governed by the laws of physics. According to this view, the universe emerged from a quantum fluctuation, where particles and energy blinked into existence out of nowhere, driven by probabilistic rules intrinsic to quantum mechanics. The initial singularity and subsequent expansion could be entirely natural phenomena, with no need for something beyond physical laws. It's as if the universe, in its infancy, followed an intricate set of rules that, once set in motion, became its own cause, leading to the cosmos observed today. However, this raises a question. Where did these laws and constants come from? Are they the product of natural processes, or do they point to a deeper, perhaps even intentional origin? This is where divine action enters. Many religious traditions see the universe's creation as an act of a divine being, a purposeful, intelligent cause that initiated existence intentionally. This includes not just the moment of creation, but also the universe's fine-tuning, the precise values of fundamental constants and conditions that allowed life to emerge, as signatures of purpose. Some believe divine action is woven subtly into reality, perhaps guiding natural processes beneath the surface, allowing complexity and consciousness to arise. Others envision divine intervention as a single act at creation's inception, setting everything into motion intentionally. Many scientists and philosophers regard divine action, especially in traditional supernatural terms, as outside empirical investigation. They focus on understanding the universe through testable natural laws, arguing that invoking divine intervention falls outside scientific methodology. Still, the question persists: can natural laws alone account for the universe's existence? Or do aspects like the specific form of physical laws point toward a deeper cause or purpose? Some cosmologists argue that initial conditions of the universe, or what they call laws of nature, might be contingent rather than necessary, hinting at something beyond physical explanation. In this debate, divine action is sometimes seen as a way to fill gaps when natural explanations seem inadequate or incomplete. Conversely, scientific progress pushes toward natural explanations, finding beauty and order in the universe's laws as emergent rather than evidence of divine design. The multiverse theory, for example, suggests our universe is just one bubble in a vast multiverse, where regions have different physical laws, implying that fine-tuning might be a cosmic lottery rather than divine intervention. At its core, the tension between divine action and natural processes isn't just science versus spirituality. It concerns how we interpret the origins and meaning of existence. Some see no contradiction in recognizing divine purpose setting the stage, with natural laws then carrying the cosmic story forward without interruption. Others view the universe solely as a product of natural causes, with no need to invoke divine presence. This ongoing dialogue reflects profound questions about where everything came from and whether there is a purpose behind it. As science delves deeper into reality's fabric and philosophy explores implications of that knowledge, the debate about divine action versus natural processes remains vibrant and unresolved, a testament to the mystery surrounding the beginning of everything. Across the vast tapestry of human belief, cultures, and faith traditions, the question of how existence began has been woven into stories, teachings, and philosophies that span millennia. These varying perspectives reflect not only differing views of the universe, but also insights into human consciousness, purpose, and the divine. In many Abrahamic faiths, Judaism, Christianity, and Islam, the beginning of everything is often described as a divine act. The book of Genesis in the Hebrew Bible narrates a world created by God in a series of divine commands, starting with the famous phrase, "In the beginning, God created the heavens and the earth." This account emphasizes a purposeful act by a sovereign creator, bringing forth order from chaos, light from darkness, and life from non-existence. The emphasis here is on an intentional creation, rooted in divine will and wisdom, transcending scientific explanations and asserting that existence is rooted in a divine mind. In Islamic tradition, the Quran similarly speaks of Allah as the creator of the universe, emphasizing that everything that exists is a sign of his will and power. The origins are seen as a deliberate act by a conscious, omnipotent being, with the universe unfolding according to his divine plan. Hinduism offers a more cyclical view of creation, rooted in the concepts of eternal rhythms and cosmic cycles. Instead of a single beginning moment, the universe is seen as periodically born, destroyed, and reborn through endless cycles. Central to this is the concept of Brahman, the ultimate unchanging reality. whose reverberations manifest into the cosmos through divine emanations involving deities like Brahma, Vishnu, and Shiva. Creation begins not from absolute nothing, but from the bubbling forth of cosmic energy that exists beyond time and space. Some interpretations see the universe as a divine play, Lila, with creation stories describing the universe as emerging from a cosmic seed or sound, Om, that sets the cosmic dance into motion. Buddhism, while not focusing on a creator deity, approaches the beginning of existence through the lens of dependent origination and impermanence. The universe is viewed as a continuous cycle of birth, existence, decay, and rebirth. Instead of an absolute beginning, the focus is on understanding the interconnectedness of phenomena, emphasizing that existence arises due to various causes and conditions coming together. This view invites contemplation on the nature of reality itself, not rooted in a divine act, but in the patterns and laws that govern existence, which are ever-changing and dependent. Many indigenous traditions carry their own stories of creation that are deeply woven into their cultural and spiritual identities. For instance, in many Native American beliefs, the world was brought into existence through the actions of spiritual beings or through sacred ceremonies. These stories often involve elements of the earth, water, sky, and animals, illustrating a profound harmony between humans and nature. Creation narratives are often poetic, emphasizing the sacredness of the land and the interconnectedness of all life. Philosophically, some traditions ponder whether the universe had a beginning at all. Certain streams of thought, like some forms of Taoism, perceive the universe as an eternal flow, without a definitive start or end, governed by the Tao, a fundamental principle that is elusive and all-encompassing. In this view, the universe's origin is less about a specific event and more about a harmonious, ongoing process of natural unfolding. In all these diverse perspectives, one thing remains clear. The question of where everything came from is deeply intertwined with each tradition's understanding of the divine, the sacred, or the fundamental nature of reality itself. Whether seen as a deliberate act of divine will, a cosmic cycle, the emergence from a cosmic sound, or an interconnected web of causes, these stories reflect humanity's enduring quest to make sense of the mystery, the origin point that sparks the dance of existence, inviting us to explore not just the universe, but our own place within it. The debate over whether a divine creator challenges or complements scientific theories has persisted throughout history, driven by our desire to understand the origins and purpose of existence. At first glance, science and religion seem opposing. Science relies on empirical evidence, testable hypotheses, and natural explanations, while the idea of a divine creator involves supernatural intelligence and purpose beyond empirical validation. This perceived dichotomy has led many to see them as mutually exclusive. However, a closer look reveals a nuanced relationship where they can both challenge and complement each other, depending on perspective. Scientific models like the Big Bang Theory describe the universe's origins as a rapid expansion from an extremely hot, dense state, governed by physical laws such as quantum mechanics and general relativity. These theories offer explanations for the universe's development over billions of years, detailing observable, testable processes, without invoking supernatural intervention. They focus on the what and how of the cosmos, providing a comprehensive account within the natural laws framework. Yet questions about the why, such as why fundamental constants are finely tuned for life, or why the universe exists at all, extend beyond mechanistic explanations. These questions touch philosophical and theological considerations. Some interpret the fine-tuning as evidence of intentional design, suggesting the universe's underlying purpose implies a creator or guiding intelligence. Others argue the universe's apparent fine-tuning might be explained through natural means, like the multiverse hypothesis or anthropic principles, which posit our universe is just one of many, with conditions suitable for life because we observe it. Considering a divine creator can challenge scientific theories by introducing an untestable supernatural element, risking an abandonment of empirical rigor. Critics say, invoking divine intervention is outside scientific methodology, as it cannot be falsified or directly observed, which are core scientific criteria. As a result, some view divine explanations as philosophical assertions, not scientific theories. However, many see science and religion as addressing different questions. Science explains mechanisms, while religion explores meaning, purpose, and moral values. For believers, scientific discoveries regarding the universe's complexity deepen awe and reinforce belief in a divine creator who imbued the universe with purpose. They argue science and faith are complementary. Science explains the how, faith explores the why. For example, some perceive the universe's fine-tuning as evidence of intentionality. Natural laws may be seen as expressions of divine will or ongoing acts of creation. Conversely, some scientists and philosophers contend theological claims go beyond scientific validation. They argue invoking divine agency reduces objectivity in science, oversimplifying the scope of scientific explanation. Science strives to explain phenomena through natural causes, leaving questions of purpose or morality to philosophy or religion. Throughout history, figures like Isaac Newton and Georges Lemaitre saw no contradiction between science and faith. Newton believed his work revealed divine order, viewing the universe as a reflection of divine wisdom. Similarly, Einstein considered scientific inquiry a means to uncover universe's profound mysteries, which could be seen as expressions of a higher intelligence. Ultimately, whether a divine creator challenges or complements science depends on individual interpretation. Some see science as unveiling natural mechanisms, with faith addressing questions of purpose and meaning. Both can coexist and enrich understanding, inspiring wonder and humility before the universe's mysteries. The dialogue between science and religion fosters a holistic view, an ongoing quest beyond empirical knowledge alone that explores profound questions of existence, motivating curiosity and reverence. In conclusion, the relationship between science and the concept of a divine creator is complex and multifaceted. They can be seen as addressing different dimensions of human understanding, the empirical and the spiritual. While science seeks to explain how the universe functions, religion often seeks to explain why it exists and what it means. Many find their perspectives compatible, viewing faith and scientific inquiry as complementary pursuits that together deepen our grasp of reality. By acknowledging their distinct roles, individuals can embrace a broader, more integrated perspective, one that respects scientific rigor, appreciates spiritual insight, and recognizes the ongoing human quest to comprehend the universe at both the mechanistic and meaningful levels. This synergy fosters a richer appreciation of the universe's mysteries and our place within it, encouraging a humble acknowledgement of the limits of knowledge while inspiring continued questions, exploration, and awe. The ongoing dialogue between science and religion thus continues to shape our understanding of existence, enriching our spiritual and intellectual journeys toward truth. Considering a universe emerging from nothing raises profound questions about existence, causality, and reality. The core dilemma is, if everything can come from nothing, what does that imply about divine creation or purposeful origin? Alternatively, does it mean the universe's existence is a remarkable accident, without reason or purpose? Many religious traditions hold that a divine being intentionally created the universe. For them, nothing isn't just the absence of everything, but the absence of potential, meaning and existence, requiring a conscious act to bring about being. If the universe arose from absolute nothingness without divine influence, what does that mean for these beliefs? It suggests the universe might be more akin to a natural quantum fluctuation, an event with no guiding hand, shifting focus from divine purpose to natural processes. This raises the question, does the universe inherently follow some fundamental principle that makes such a leap from nothing to something inevitable or statistically possible? But what is nothing philosophically? Is it an absolute void? No laws, no space, no time? Or is it a quantum state of possibilities? A fertile ground where the seeds of reality lie hidden? If the latter, the boundary between nothing and something blurs, complicating implications, it suggests nothing could be rich with potential, a prelude rather than pure absence. Under this view, the universe's emergence might be a natural unfolding of reality's fabric, where the distinction between nothing and something dissolves. This leads to questions of necessity and contingency. Is the universe necessary, bound by some fundamental law, or contingent, dependent on specific initial conditions or chance? If the universe could have been different or might not have existed at all, then its existence appears to be a cosmic accident. This raises profound questions about necessity in the cosmos. Are we to believe the universe has no ultimate reason for being, existing only as a play of probabilities and laws that happen to produce our reality? Or does its existence point towards some deeper, possibly unknowable principle underpinning it all? The idea of a multiverse, countless universes with varying laws, amplifies these philosophical questions. If every universe emerges with different conditions, ours might just be a lucky or inevitable outcome amid an infinite cosmic lottery. Philosophically, this challenges notions of uniqueness and purpose. Are we special, or just an improbable blip in an endless sea of possibilities? The question of meaning follows. If everything can arise from nothing, does that diminish human significance, our pursuits, hopes, or does it inspire awe, suggesting that even in accidents, there's mystery and grandeur beckoning us to explore? Embracing a universe born from spontaneous origins may lead us to view meaning not solely from origins, but through relationships, consciousness, and our ongoing search for understanding. Our pursuit of knowledge becomes a response to the universe's profound silence, an act of seeking amid uncertainty. Contemplating a universe from nothing opens a Pandora's box of issues: causality, necessity, purpose, and the structure of reality itself. It urges us to reconsider whether existence is an accident or something beyond human comprehension. Some argue that ultimate truths remain forever beyond our grasp. Others find that this mystery fuels our drive to reason and explore. It suggests some aspects of the cosmos may be inherently unknowable, yet the quest to understand remains meaningful. In the grand scheme, the idea that the universe emerged from nothing challenges foundational assumptions about its origin. It raises the possibility that existence might be a spontaneous event, pointing to a deeper principle, one beyond human understanding. This perspective urges acceptance that some mysteries may forever stay hidden, yet motivates continued questioning. The notion of a universe born from nothing compels reflection on causality, purpose, and the fabric of reality. While it may imply that the universe is an accident, it also opens the door to ideas of deeper, possibly divine or fundamental, principles at play. Such contemplation underscores the limits of human knowledge, yet fosters our endless curiosity. The search for meaning persists amid cosmic silence. As we explore these questions, they reaffirm the human spirit's resilience, our unending desire to find purpose and understanding in the vast, mysterious universe we inhabit. The idea of nothing challenges human curiosity and existential thought, because it confronts us with an absence so profound that it defies our instincts to understand or imagine it. When we think of nothing, we often picture a void, a vacuum or emptiness. Yet the concept is far more complex. It questions our deepest assumptions about existence, causality, and reality itself. Our minds seek explanations to find meaning and purpose, but nothing makes this search unsettling, even paradoxical. If everything, matter, energy, space, time, originated from nothing, then this nothing must have held some potential to give rise to everything. How can emptiness, a non-being, be the source of being? That question challenges fundamental philosophies about existence, and causes us to consider whether nothing is truly void, or if it contains qualities beyond current understanding. One of the biggest challenges nothing presents is the idea of origin. Traditional narratives describe creation as divine will, a cause outside or beyond the universe. Modern physics, however, suggests a universe emerging from quantum fluctuations, tiny, fleeting disturbances in the vacuum state. In this view, nothing ceases to be mere emptiness and appears as a dynamic, unpredictable field full of potentialities. Nothing becomes more like fertile ground than an absolute void, a quantum potential rather than pure emptiness. This shifts thinking about causality and origins. Instead of a cause-effect chain from divine acts or pre-existing conditions, the universe might have spontaneously emerged from quantum froth, a form of nothing. But does this imply nothing is truly nothing? Could it be a precondition, a balanced state from which all possibilities arise? This halts us because it forces a re-examination of what nothing entails. Is it a void, or a fertile ground brimming with potential? The concept destabilizes the understanding of the universe's beginning. Moreover, nothing destabilizes our sense of stability. It challenges us to accept that a coherent, ordered universe could be a rare, improbable emergence from an almost inconceivable abyss of non-being. If everything can come from nothing, what does that imply about the universe's fragility? This idea shatters the comforting notion of a universe created with purpose or divine intent. Instead, it suggests a universe arising from chance, randomness, and quantum phenomena, making reality less predetermined and more a product of instability. This perturbation profoundly affects worldview. It urges us to reconsider meaning in a universe lacking an ultimate cause or purpose, merely chaos transforming into order on larger scales. Some quantum cosmology theories propose that the universe's fabric is a fleeting emergent phenomenon, an illusion of stability arising from chaos. This challenges the idea of a universe designed or purposeful, suggesting instead that it's an outcome of natural laws, quantum effects, and indeterminacy. Grappling with nothing leads us to reflect on our place in the cosmos. If everything emerged from nothing, if existence is spontaneous, then perhaps nothing is not an absence but a fundamental aspect of reality. It could be the source of all potential, the ground from which everything arises. Understanding nothing might hold the key to answering why anything exists rather than nothing, addressing profound mysteries of existence. Confronting nothing urges us to rethink the universe's foundation. It invites us to see the universe not as a designed creation, but as an enigmatic outcome of natural laws, quantum phenomena, and indeterminacy. This challenges our understanding of reality, an invitation to embrace the mystery at the core of being. In contemplating nothing, we grapple with the idea that the universe might be an emergent, fleeting phenomenon, arising from chaos rather than purpose. The true nature of nothing is far more complex and rich than simple emptiness. It compels us to accept that reality may be less stable, more probabilistic, and deeply intertwined with the profound and puzzling concept of nothingness itself. The question of whether the universe can be infinite in the past or future has puzzled thinkers across ages, blending science, philosophy, and metaphysics. Asking if the universe is infinite in the past probes whether there was an unending chain of events before what we consider the beginning of time itself. Conversely, contemplating an infinite future considers if the cosmos will continue forever, endlessly evolving or winding down into some ultimate ending. To understand whether the universe might be infinite in the past, imagine a calendar stretching infinitely backwards, a never-ending timeline with no starting point. Traditional Big Bang cosmology suggests our universe began about 13.8 billion years ago, in an initial singularity. This implies a beginning in time. There was no before the Big Bang because time itself sprang into existence then. Asking what happened before the universe is like questioning what's north of the North Pole, an unintelligible question within current frameworks. However, some cosmologists entertain models where the universe is eternal in the past. For example, the cyclic universe model proposes endless cycles of expansion, contraction, and rebirth through Big Bangs, suggesting an infinite past. Another idea from quantum cosmology states the universe might have no beginning at all, existing as a quantum fluctuation within a multiversal landscape. In such scenarios, the concept of a finite or infinite past becomes murky, as the arrow of time may break down, or the universe's history could stretch back infinitely in eternal recurrence. Philosophical arguments like Zeno's paradoxes also question whether an infinite regress can exist in reality or only in theory. If the universe's history were truly infinite, some argue it might lead to logical paradoxes, especially when considering traversing or conceiving of an infinite sequence of events or states. Modern physics often sidesteps this, suggesting our universe's beginning may resemble a boundary, a space-time edge, rather than an infinite regress of causes. Regarding the future, the universe's infinity is perhaps easier to imagine. If the universe keeps expanding, especially with dark energy and accelerating expansion, then it could continue forever. That would mean the future is infinite, a horizon with galaxies drifting apart, stars burning out, and structures fading. In this view, the universe might become a cold, lonely place, culminating in heat death, where entropy maximizes and no meaningful change occurs. Could the universe truly be infinite in the future? That's uncertain. Physics suggests that continuous unbounded expansion could lead to cosmic exhaustion, stars burning out, black holes evaporating, entropy peaking. Yet, undiscovered physical processes, or a multiverse with more complex structure might alter this outlook. The future could be more unpredictable, possibly cyclical or episodic rather than endless. All these ideas highlight an ongoing mystery. Our current scientific theories are powerful but incomplete. They can accommodate both an infinite future, if expansion continues, and the possibility of a finite or no beginning in the past, under different models. Whether the universe is infinite or not in either direction touches core questions about existence. These questions challenge human understanding and inspire curiosity to explore beyond what is visible, measurable, or conceivable. The universe's remarkable fine-tuning is one of the most intriguing puzzles in the story of existence. Imagine the universe as a kind of cosmic lock, with the right combination of factors that have to align perfectly for life as we know it to flourish. If any of these parameters had been slightly different, the universe might be a completely different place, perhaps a cold, sterile void, devoid of stars, planets, and life. The significance of this fine-tuning isn't just about the numbers lining up. It challenges us to understand the fundamental reasons behind these uncanny coincidences. Take, for example, the strength of the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Each of these plays a critical role in shaping the universe's structure. Gravity must be fine-tuned so that stars can form, but not so strong that the universe collapses on itself. If gravity had been just a little weaker, galaxies might never coalesce, leaving no places for planets or life to emerge. If it had been stronger, everything might have imploded into dense black holes before life had a chance to develop. Similarly, the balance between the forces governing atomic nuclei is precisely calibrated. If the strong nuclear force was slightly weaker, the universe would lack the necessary elements like carbon, which forms the basis for so much life. Slight variations in the electromagnetic force could prevent atoms from holding together, making complex molecules impossible. In essence, the universe's parameters seem almost unnervingly exact. It begs the question, why should these values be so perfectly arranged? Several explanations have been proposed. One is the idea of a multiverse, a sprawling collection of universes, each with its own set of physical constants. In this view, ours might just be one of countless universes, and by chance alone, it turned out to have the right conditions for life. But this leads us into a territory that's difficult to test or verify, making it a controversial and philosophical proposition as much as a scientific one. Another perspective is that of design or purpose. To some, the fine-tuning hints at a cosmic architect, a creator who set these parameters deliberately to allow life to exist. It's a view that resonates with various religious traditions which see the universe as a purposeful creation. Yet critics argue that fine-tuning could simply be an emergent property, an outcome of natural laws that we have yet to fully understand. Perhaps the universe's constants are not arbitrary at all, but are necessary conditions derived from deeper principles we haven't discovered yet. The significance extends beyond pure curiosity. Why does the universe seem so hospitable to life? Is it a mere coincidence, or is there some underlying reason for this delicate balance? This question fuels debates across science, philosophy, and theology. It raises profound questions about the nature of existence itself, whether the universe's fine-tuning points to some grand design, or reflects a natural, unavoidable consequence of the fundamental laws of physics. It even pushes us to reconsider what we mean by nothing. If even the very fabric of the universe requires such precise conditions, perhaps nothing was never truly just empty absence, but a state with the potential for these astonishing properties. The big picture is that the universe's fine-tuning invites us to reflect on the nature of reality and our place within it. Are we simply lucky survivors in a universe that almost wasn't? Or are we witnesses to a universe that was carefully set in motion with intention? As science advances and our understanding deepens, hopefully, we'll come closer to unraveling this mystery. Yet, perhaps the beauty of the question is that it challenges us to keep exploring, to keep searching for that elusive answer that connects everything, up to and including our very existence. The idea of creation from nothing has long intrigued philosophers, theologians, and scientists. When asking if it's scientifically meaningful, we enter a complex intersection of physics, cosmology, and metaphysics. To understand this, we must consider what science can say and where it encounters limitations. Classical physics viewed nothing as an absolute void, empty of matter, energy, and laws. This straightforward definition suggested that nothing could come from nothing. However, modern physics challenges this. Quantum field theory shows that even the emptiest space isn't truly nothing. It's filled with quantum fluctuations, temporary energy changes that occur spontaneously, even without particles or matter. This raises the key question: could these fluctuations be the something that ignited the universe? Some hypotheses propose that the universe originated from a quantum fluctuation in a pre-existing quantum field. In this view, the universe's emergence isn't from absolute nothing but from quantum potentiality. Yet, this introduces further questions. What is the quantum field itself? Can it exist without a foundation? Is the quantum vacuum truly nothing, or just a different form of something, a chaotic, fluctuation-filled field? Cosmic inflation theories suggest our universe might be a bubble in a multiverse, with countless universes emerging through similar quantum processes. In this scenario, the universe's origin isn't from absolute nothing, but from quantum fields within an eternal multiverse. The question then becomes, is the multiverse itself something, complicating the idea of a universe arising from nothing? If the multiverse exists, the idea of initiating from total nothing becomes less clear. Moreover, cosmologists explore boundary conditions, whether the universe began in a low-entropy special state that set its evolution. Some models propose the universe could have emerged spontaneously from a quantum state governed by unknown laws, but if these laws only came into existence with the universe, can they be considered part of nothing? Or are they fundamental features present from the start? Counterintuitively, some physicists argue that asking if the universe came from nothing is a category mistake. Because nothing may be incompatible with quantum conditions of the early universe, it's more meaningful to frame the question as regarding something, a state governed by laws, principles, and conditions, even at the universe's inception. Does science have a definitive answer? Not quite. The concept of creation from nothing remains more a philosophical issue than a strictly scientific one. Physics can describe models where the universe emerges from quantum potentialities or fluctuations, but whether these models depict creation from absolute nothing or from a prior something remains unresolved. Every theory offers insights into the conditions preceding the universe's birth, but the ultimate origin behind those conditions still eludes us. Ultimately, the scientific inquiry into creation from nothing challenges our understanding of nothing. It blurs the boundary between empirical science and philosophy, reminding us that some questions may be forever beyond experimental reach. Yet these questions are profound. The origin of everything may be an enigma woven into the fabric of existence, something science can describe in part but perhaps never fully explain. Certain origins might be inherently unknowable, limited by human understanding and the tools of science. This mystery invites ongoing reflection and exploration. It pushes the limits of knowledge, forcing us to confront the nature of reality and the boundaries of scientific explanation. While physics offers models of quantum beginnings, whether these represent creation from nothing or something remains uncertain. The concept challenges us to rethink what nothing truly means, revealing that some questions about origins may forever be beyond scientific resolution, yet they continue to shape our pursuit of understanding. As the quest to understand the universe's origins continues, scientists are pursuing ambitious projects that might shed new light on this ancient mystery. These efforts include advanced telescopes, innovative particle accelerators, and sophisticated computational models, all aiming to probe the earliest moments of existence and perhaps glimpse what preceded the Big Bang. One major initiative is the development of next-generation space telescopes. The James Webb Space Telescope has already looked deeper into the universe's history than any before, capturing faint, ancient light from galaxies formed billions of years ago. Future telescopes like the Nancy Grace Roman Space Telescope and ESA's Euclid are designed to map the universe's geometry and explore dark energy. Understanding how the universe expanded in its early moments may reveal clues about what triggered that expansion. Did a quantum fluctuation cause the Big Bang? Could exotic forms of energy or matter have played roles in setting the stage for everything we see today? On Earth, large particle accelerators are also advancing. CERN's Large Hadron Collider, planning higher energies to recreate conditions fractions of a second after the universe's birth, seeks to identify particles and forces that shaped those primordial moments. These experiments aim to find remnants of the processes behind cosmic inflation or the Big Bang itself. Discoveries of fundamental particles could unlock understanding of how the universe emerged from a quantum state, or reveal mechanisms that drove its rapid early expansion. Meanwhile, gravitational wave observatories like LIGO and Virgo are enhancing their sensitivity, allowing detection of spacetime ripples caused by violent cosmic events. Analysing gravitational waves from the universe's earliest moments, such as black hole mergers shortly after its birth, could provide direct evidence about initial conditions. Researchers are exploring ways to observe primordial gravitational waves, faint echoes predicted by cosmic inflation theories. Detecting these signals would open a window into quantum fluctuations that possibly seeded galaxies. In addition, theoretical and computational approaches are advancing rapidly. Supercomputers now simulate early universe conditions, exploring scenarios where space might have undergone phase transitions. These models test alternative origins like cyclic models, where the universe rebounds after collapse, multiverse theories suggesting our universe is one among many, or quantum bounce models, proposing a universe that cyclically expands and contracts without a beginning. Such simulations help refine hypotheses and suggest observable signatures for future experiments. Overall, these interdisciplinary efforts, merging observation, particle physics, and simulation, are gradually uncovering layers of cosmic mystery. In the coming decades, they may reveal evidence that points beyond a singular beginning, suggesting a universe part of an eternal evolving fabric. Alternatively, they might confirm that origins remain hidden within the deepest cosmic layers, woven into the fabric of spacetime itself. This pursuit of understanding, driven by relentless curiosity, brings us closer to answering whether the universe's origin was a sudden spark from nothing or something far more complex and astonishing. These endeavours, advanced telescopes, high-energy colliders, and sophisticated simulations, are central to revealing the truth about our universe's beginnings, and perhaps its true nature beyond the Big Bang. Word count, 523. Advances in quantum cosmology threaten to upend everything we think we know about the universe's origin. Imagine peeling back layers of an onion, only to find a reality far stranger than our current models suggest. Every experimental and theoretical breakthrough could rewrite the story of how everything came to be, from the absolute nothingness that fills our imagination with awe and mystery. Today, quantum cosmology operates at the boundary where quantum mechanics and general relativity collide. Quantum physics explains the tiniest particles and fields, while Einstein's gravity governs the cosmic scale. But combining these frameworks reveals a world where space and time may become quantized, granular, or even emergent from more fundamental pre-geometric structures. These insights could allow scientists to glimpse the universe's earliest moments, not as a single catastrophic beginning, but as a complex, possibly cyclical pattern woven into the fabric of time. One of the most tantalizing prospects is resolving the singularity, the point of infinite density and temperature where classical physics breaks down. Imagine a universe that didn't erupt from a single point, but emerged from a quantum bounce. Such a bounce suggests the cosmos expands, contracts, and then rebirths in an eternal dance. Instead of a universe with a definite start, it could be part of infinite cycles or multiverses, interconnected within a vast cosmic landscape. This shifts our perspective from a universe born out of nothing to one existing within an extended, possibly eternal quantum realm that endlessly spawns new universes. Advancements might also help us understand the quantum state from which our universe arose. If the universe is a quantum fluctuation among potentialities, then uncovering how these potentialities crystallize into matter, energy, and space-time could transform our view of existence. The boundary between nothing and something might be much blurrier than previously thought, a continuum rather than a clear line. The fabric of reality could be a product of quantum probabilities collapsing into structure, giving rise to space and time from a primordial quantum haze. Furthermore, breakthroughs could illuminate the multiverse hypothesis, the idea that our universe is just one bubble among countless others. Quantum effects might give rise to multiple branching universes, making our universe merely one node in an infinite web of realities, each with different physical laws. This could fundamentally alter our understanding of our place in the cosmos, no longer the center of a universe created from nothing, but part of a boundless multiverse, interconnected through the probabilistic laws of quantum mechanics. Ultimately, as quantum cosmology refines its theories and tools, be it through quantum simulations, gravitational wave observations, or data from particle physics, our perspectives might expand beyond classical understanding. We could come to see the universe's origin not as simple creation from nothing, but as a quantum emergence from potentiality, woven by probabilities and cycles. These advances may unveil secrets that challenge our deepest philosophical assumptions, revealing that what we once considered nothing was actually a fertile quantum ground, the true birthplace of everything. The question of ultimate causality delves into core philosophical issues, challenging our understanding of existence, cause, and reality itself. It asks, what is the fundamental origin of everything? Is there a first cause, or is there an infinite regress of causes, each leading to another indefinitely? These questions have puzzled thinkers for centuries. One major challenge is the debate between a first cause and an infinite regress. If everything has a cause, what caused the initial cause? Some argue that an uncaused cause must exist, something necessary and outside causality, often identified as a divine or necessary being. Others claim that the very idea of a first cause is flawed, because causality might not be fundamental but a human way of understanding the world. Understanding causality itself presents difficulties. In everyday experience, causes precede effects. But in quantum physics, causality becomes blurred. Particles can influence each other instantaneously across space, violating the classical notion that causes come before effects linearly. This raises questions. Is causality a fundamental feature or merely an emergent property of classical physics? If the latter, then seeking an ultimate cause might be misguided, as causality could arise from deeper principles we have yet to grasp. Another philosophical challenge involves nothing, not just emptiness, but true non-being. If anything exists, how can it emerge from nothing? Some argue nothing doesn't truly exist. Instead, it's a state of potentiality or a quantum vacuum orbiting with possibilities. This complicates the distinction between nothing and something, making the quest for an ultimate cause more tangled. Perhaps the universe always existed in some form, or the question is flawed because our understanding of existence is limited. The philosophical debate about whether ultimate causality is comprehensible adds another layer. Some suggest humans can only understand causes within the universe, but not at its origin. Asking, what caused the universe, may be meaningless, because causality as we know it might only apply inside the universe. If time began with the Big Bang, then asking about a cause before it might be nonsensical. The idea of a necessary being or first mover raises metaphysical questions that cross into theology and existential philosophy. Does positing such an entity resolve the problem or simply push it back? Does it provide a satisfying explanation or shift the mystery elsewhere? When examining origins, are we applying human notions of causality where none may be relevant? Could our questions be inherently limited by mental frameworks? Ultimately, grappling with ultimate causality is about understanding the limits of our knowledge and the foundations of reality. It challenges our assumptions. Does the universe need a cause? Is causality fundamental or emergent? Can the human mind comprehend such mysteries? These questions compel us to explore whether causality applies at the universe's boundary, whether it's a human construct, or whether the very notion of a cause for existence is an illusion. In questioning, we confront whether our concepts of causality and being are sufficient to explain the universe's origin. The mysteries remain profound, pushing the boundaries of philosophy and science alike. As we explore the universe's origins, a key question arises. Could new physics finally reveal an initial cause or a first mover? For centuries, thinkers pondered whether the universe had a definite starting point, a moment when everything transitioned from nothing into something through an uncaused cause or an initial spark. But with advances in physics, especially in quantum mechanics, string theory, and quantum gravity, the answer might be more complex and more fascinating than ever imagined. In classical physics, the idea of a first cause seemed natural. Newtonian mechanics implied a universe ticking forward based on initial conditions set at the start. However, it didn't explain what caused those initial conditions. Was there an uncaused cause? Did something cause everything? These questions fueled philosophical debates about whether the universe was created by a necessary being emerged from a void, or was simply eternal. Today, our understanding is changing. Quantum physics suggests a universe far from the static void once envisioned. Instead, spacetime appears as a turbulent foam-like fabric where particles flicker into and out of existence, obeying probabilities rather than certainties. Could nothing actually be a quantum state full of potentialities? If so, the universe might not have arisen from an absolute void, but from a quantum condition, an ocean of potential that unfolds into reality. This view opens new possibilities for physics to redefine our origin story. Approaches like loop quantum cosmology propose a bouncing universe, avoiding a traditional beginning. Instead of a single starting point, there might be cycles of contraction and